A single flash in the data held more power than the sun emits in days. This was the first glimpse of a fast radio burst, one of the most profound and energetic mysteries in modern astronomy. We are about to dive into 50 of their deepest puzzles, from their mind-boggling origins to their bizarre, repeating patterns. By the end, you will grasp how these millisecond flashes from across the cosmos hold secrets that could rewrite the rules of physics and the story of the universe itself. How can something lasting less than a blink release such catastrophic energy? And what is causing these signals to arrive in strange, predictable cycles? The answers are hidden in the static. What do you think it will take to finally solve a cosmic mystery this vast? That first flash was not witnessed in real time. It was a ghost waiting in old data. In 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through archival recordings from the Parkes Radio Telescope in Australia, a routine search for distant pulsars. They were not hunting for cosmic explosions. Buried in the static from 6 years prior was a spike of radio waves so intense, so brief, it had been automatically dismissed as terrestrial interference. But this was different. It lasted just 5 milliseconds, a blip shorter than a camera's shutter click, yet it carried the unmistakable fingerprint of a signal that had traveled across the universe. The energy was staggering, equivalent to the sun releasing its entire output over several days, but compressed into a fraction of a second. The data pointed to a source billions of light years away, far beyond our Milky Way. When Lorimer and his team published their findings, naming it the Lorimer Burst, the reaction was not instant celebration but profound skepticism. Could a telescope really detect something so powerful from such an impossible distance in a mere instant? Many senior researchers were convinced it had to be a glitch in the electronics, or perhaps a secret military satellite, anything but a genuine astrophysical event from the deep cosmos. This single, controversial point of light, discovered by accident in old data, refused to be explained away. It was the first clue, the crack in the door, that forced astronomers to confront a reality they had not even considered possible. The field of fast radio burst research was born not with a bang heard around the world, but with a quiet, persistent mystery hiding in plain sight. The sheer violence of that first signal defied all expectations. This is the second great mystery, the staggering and almost incomprehensible energy packed into a fast radio burst. To truly grasp it, consider our own sun, a nuclear furnace that has burned steadily for over 4.5 billion years. It bathes our entire solar system in light and heat, its energy output defining life itself. Now, imagine the sun releasing its total power not over millennia, not over a year, but over several entire days, and then compressing all of that furious energy into a radio flash lasting just 5/1000ths of a second. That is the scale we are talking about with a typical fast radio burst. It is a cosmic particle beam of unimaginable ferocity, a scream of radio waves so intense it can be heard across billions of light years. The most extreme events, like one designated FRB 2022-0610A, detected in 2022, are even more baffling. This single burst, over in a millisecond, released as much energy as our sun will emit over 30 years. Astronomers describe this using a term called isotropic equivalent energy. In simple terms, it is a way of calculating the total power if the burst exploded equally in all directions, like a perfectly spherical bomb. The fact that we can detect these signals from such cosmic distances means their isotropic energy must be astronomically high, implying an engine of almost perfect, terrifying efficiency. The challenge this poses to physics is monumental. What natural process in the universe can possibly concentrate the equivalent of a stellar lifetime into a blink so brief? It rules out almost everything we know. It is not a simple stellar explosion, not the collision of two asteroids, not even the steady spin of a pulsar. The engine behind a fast radio burst must be something far more exotic, something capable of harnessing gravity or magnetism on a scale we have barely begun to understand. This single millisecond is a signature of cosmic violence unlike any other, a fingerprint left by a phenomenon that bends the very rules of energy itself. Yet that incredible power tells only half the story. The other half is written in the journey the signal took to reach us, a journey measured not in miles but in a strange, smearing effect. Astronomers call this the dispersion measure, and it became the key to unlocking the third great mystery, the true cosmic distance of these bursts. Imagine a fast radio burst as a chorus of different radio notes, all emitted at the same precise instant from a source far, far away. As this chorus races through the vast, nearly empty spaces between galaxies, it encounters a thin soup of free electrons, a plasma that fills the universe. This plasma acts like a cosmic prism for radio waves. The higher frequency notes, the ones with a higher pitch, slip through a little faster. The lower frequency notes, the deeper tones, get slowed down just a bit more. Over an immense journey, this tiny difference adds up. By the time the entire chorus of the burst reaches our telescopes, it is no longer a single sharp crack. It is a smear. The high notes arrive first, followed milliseconds later by the low notes, creating a distinctive downward swoop in the data. The greater the smear, the more plasma the signal has traveled through, and therefore the greater the distance it has come from. This dispersion measure is like a cosmic odometer reading etched into the signal itself. For the earliest bursts, this reading was shockingly high. The Lorimer burst's dispersion measure pointed to a source billions of light years beyond our Milky Way. But here is where the controversy ignited. Could that high reading be a trick? What if the burst came from much closer, from within our own galaxy, but simply passed through an unusually thick local cloud of plasma? For years, this debate raged. Skeptics pointed to a few bursts with lower dispersion measures that could, theoretically, be explained by sources within the Milky Way's halo. The community was split, with one camp convinced we were seeing cataclysms in distant galaxies, and another suspecting we were merely studying bizarre, local stellar phenomena. The debate was only settled with the discovery of the repeaters. When astronomers finally pinpointed the location of a repeating fast radio burst to a specific, tiny galaxy billions of light years away, it was definitive proof. The dispersion measure was not a local illusion. It was a true measure of an epic voyage. These millisecond flashes were not from our celestial backyard. They were intergalactic travelers, carrying with them the faint imprint of every electron cloud they had passed through on their billion-year journey to Earth. That single, definitive distance measurement settled one debate but immediately opened another, far stranger one. Astronomers now knew these bursts were coming from distant galaxies, but they still had no idea what was making them. Were they all the result of a single, catastrophic explosion, a stellar death scream so final it could only happen once, or could something survive the blast to fire again? This leads us directly into the fourth great mystery, the fundamental split in the fast radio burst family, repeaters versus one-offs. For nearly a decade after the Lorimer burst, every new detection was a solitary event, a cosmic flash in the pan. Each one seemed to support the idea of a cataclysmic source, something that obliterated itself in the process, like two neutron stars colliding or a star being shredded by a black hole. The universe, it seemed, was filled with these brilliant, one-time fireworks. Then, in 2016, everything changed. Researchers using the giant Arecibo radio telescope in Puerto Rico were monitoring a patch of sky where a fast radio burst had been seen years earlier, designated FRB 121102. To their astonishment, they saw not one but multiple new bursts coming from the exact same point in space. This was not a mistake. The signal was repeating. The discovery was monumental. It meant the source of these bursts was not destroyed. It had to be an object of immense durability, something that could unleash these titanic energies over and over again, like a cosmic lighthouse with a broken switch. Suddenly, the theoretical landscape fractured. Repeaters pointed strongly to objects like highly magnetized neutron stars called magnetars, which could have colossal starquakes on their surfaces, or to bizarre interactions in the accretion disks of black holes. One-off bursts, however, still suggested final, violent mergers. The most puzzling question now is whether this split is even real. Are there two completely different cosmic engines at work, one that repeats and one that does not? Or could all fast radio bursts be repeaters, just on wildly different schedules? Some sources might fire every few hours, while others might slumber for centuries between outbursts. We simply have not been watching long enough to know. This duality lies at the heart of the modern hunt, forcing us to ask if we are witnessing two different kinds of cosmic violence, or merely two different expressions of the same profound and hidden physics. Pinpointing the origin of a millisecond flash from billions of light-years away is a task of almost impossible precision. A single radio telescope, like the one that found the Lorimer burst, can tell us a signal arrived and give us a rough sense of its distance from the dispersion smear. But the patch of sky it points to is enormous, often containing thousands of faint galaxies. It is like hearing a single, sharp crack of thunder and trying to determine which specific house in a distant city shrouded in fog slammed its door. To solve this, astronomers had to think bigger than a single dish. They turned to interferometers. This technique links multiple radio telescopes, sometimes separated by continents, into one virtual Earth-sized instrument. Networks like the Deep Synoptic Array in California or the Australian Square Kilometre Array Pathfinder ASKAP work by listening for a burst simultaneously. When the same fleeting flash washes over each separate dish, the tiny differences in its arrival time, down to the nanosecond, are combined. Through exquisite timing, these arrays can triangulate the burst's position to a tiny dot on the sky, an area millions of times smaller than what a single telescope could manage. The process is a high-stakes race against time. First, the interferometer's rapid alert system must catch the burst in the act. Within seconds, its precise coordinates are sent out to observatories around the world. Then, giant optical telescopes like the Keck Observatory in Hawaii or the Very Large Telescope in Chile swing into action. They point their mirrors at that tiny dot, taking deep images to see what galaxy, what stellar neighborhood is lurking there. This is the moment of truth, when a faint, smudged galaxy appears exactly where the radio flash came from. The burst is localized. Why go through all this trouble? Because the host galaxy is a treasure trove of context. It tells us what kind of cosmic environment breeds these explosions. Is it a young, star-forming galaxy, chaotic and violent? Or an old, quiet one where stellar fireworks are rare? Most crucially, the optical telescope can measure the galaxy's redshift. As the galaxy's light stretches across the expanding universe, its spectral lines shift toward the red end of the spectrum. The amount of that shift gives us the true, precise distance, converting the dispersion measure's estimate into a firm cosmic address. Without this precise localization, a fast radio burst is just a brilliant mystery. With it, the mystery gains a home, a history, and a place in the grand story of the cosmos. Those precise cosmic addresses have revealed a surprising and confusing diversity. The galaxies that host fast radio bursts are not all the same. In fact, they seem to defy our expectations at every turn. We have found them in massive, tranquil galaxies, old and metal-rich, where the furious birth of new stars has long since quieted. We have also found them in the exact opposite, in tiny, chaotic dwarf galaxies, no bigger than a satellite of our Milky Way, yet blazing with the intense light of newborn stars. This is the sixth mystery, the puzzle of the host galaxy environments. It forces us to ask what kind of cosmic neighborhood is required to build an engine capable of such staggering, focused violence. The very first repeater ever localized, FRB 121102, provided a crucial and bizarre clue. Its home is a modest dwarf galaxy over 3 billion light-years away, a place buzzing with star formation. But within that galaxy, astronomers found something even stranger using the Very Large Array radio telescope. Right at the spot of the burst is a persistent, steady source of radio waves. It is not flashing, it is just constantly glowing. This suggests the fast radio burst source is embedded in a nebula of its own making, a cloud of energetic particles and magnetic fields, perhaps the remnant of a previous, even more colossal explosion. It is like finding a blinking lighthouse sitting in the middle of its own permanent, radiant fog. This persistent radio source strongly hints that this particular repeater is a young object, perhaps a highly active magnetar born from a recent supernova, still surrounded by the chaotic debris of its own violent birth. Yet other localized bursts tell a different story. Some come from the calm suburbs of big spiral galaxies, far from their busy centers. Others appear in galaxies that show no signs of recent star formation at all. This diversity is deeply confusing. If all fast radio bursts came from young magnetars, we would expect them only in galaxies that are actively making stars, because massive stars live fast and die young. The fact that they also appear in quiet, elderly galaxies suggests a second pathway. Perhaps in these places, the engines are older, like neutron stars that have wandered for eons before suddenly reactivating, or collisions between ancient, dense stellar corpses like white dwarfs. The host galaxies are not giving us a single, clear answer. Instead, they are presenting us with a menu of possibilities, each environment whispering a different story about how the universe concentrates energy into a millisecond flash. This means the true answer might not be one single cosmic cataclysm, but several, with nature finding multiple terrifying ways to create the same brilliant, fleeting signal. The diversity of host galaxies points to multiple cosmic engines, but one candidate has emerged from theory to become a frontrunner, especially for the repeating signals. This is the seventh mystery, the compelling but incomplete connection to magnetars. To understand a magnetar, you must first picture a neutron star, the collapsed core of a giant star, so dense that a teaspoon of its material would weigh as much as a mountain. Now take that object and twist its magnetic field to almost unimaginable levels. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's. A magnetar's field is another 1,000 times stronger than that. These fields are so intense they literally warp the structure of space around the star, creating a prison of unimaginable forces. The crust of the star is under constant titanic strain. Think of it as a brittle shell locked in a gravitational and magnetic vise. Every so often, that crust can crack. A starquake on a magnetar is not like an earthquake on Earth. It is a global seismic event that releases more energy than our sun emits in 100,000 years, all in a fraction of a second. The theory is that such a catastrophic snap could launch a blast of particles and energy, funneled by those insane magnetic fields into a tight beam, creating the brilliant radio flash we see as a fast radio burst. For years, this was just an elegant idea. Then, in April of 2020, the universe provided a smoking gun. A known magnetar within our own Milky Way galaxy, named SGR 1935+2154, suddenly woke up. It had been a known source of soft gamma-ray bursts, but this time radio telescopes caught something new. Alongside its high-energy outburst, it produced a millisecond-long blast of radio waves. For the first time ever, we witnessed a fast radio burst, or something very much like one, coming from a confirmed magnetar right in our cosmic neighborhood. The discovery sent shockwaves through the astronomy community. It was definitive proof that magnetars could produce these signals, yet in the same moment it deepened the mystery. The burst from our galactic magnetar, while powerful, was thousands of times weaker than the faintest fast radio bursts we detect from other galaxies. If this was the same phenomenon scaled up, the energy required from a distant magnetar would be almost incomprehensible. It forces a critical question. Can magnetars in those faraway galaxies truly produce bursts millions of times more energetic than the one we saw at home? Some scientists believe they can, through even more violent starquakes or through a process called magnetic reconnection, where the field lines snap and reconfigure in a cataclysm that dwarfs anything we have seen locally. Others wonder if the galactic burst was just a whisper, and that the true cosmic sirens require a magnetar in an even more extreme environment, perhaps one freshly born from a supernova and still swaddled in a dense nebula, or one orbiting a black hole. The magnetar connection is a crucial piece of the puzzle, a proven source in our backyard. But its faint voice compared to the distant shouts tells us we are still missing a fundamental part of the story, a hidden amplifier or a more violent chapter in the life of these magnetic monsters that we have yet to witness. But if magnetars are the leading suspects, then one specific source stands out as the strangest and most informative case file in the entire investigation. This is the curious and confounding story of FRB 121102, the original repeater. Its discovery at the Arecibo telescope did more than just prove these bursts could happen more than once. It revealed a source of almost willful unpredictability. After its initial flurry of activity, it fell silent for years, leading many to wonder if it had finally died. Then, without warning, it roared back to life, erupting in a storm of bursts, sometimes firing over 100 times in a single hour. It was not just repeating, it was having violent, episodic tantrums. The breakthrough came when the combined might of the Very Large Array and other telescopes finally pinned down its cosmic address. It lived in a tiny, unassuming dwarf galaxy over 3 billion light-years away, a place where stars were being forged at a furious rate. But the real shock was what they found at the exact spot of the bursts, a faint but steady glow of radio waves. This persistent radio source was like a campfire that never went out, sitting right where the brilliant flashes kept igniting. It suggested the fast radio burst engine was sitting in the middle of its own wreckage, a permanent nebula of energetic particles perhaps created by a supernova that birthed a young, hyperactive magnetar. This source seemed to be a teenager of the cosmos, reckless and loud, still surrounded by the chaos of its own birth. Then it did something no other fast radio burst had ever done. In 2020, as astronomers watched one of its radio outbursts, they saw a concurrent, brief flicker of X-rays. For a split second, the source screamed across more of the electromagnetic spectrum. This was a vital clue, as X-rays are a hallmark of the extreme magnetic processes thought to occur on magnetars. Yet, for all its fame and intense study, FRB 121102 remains an outlier. Later discovered repeaters often lack that persistent radio glow. They appear in different types of galaxies. Their bursts can be more sporadic or more structured. So we are left to wonder, is this original repeater the prototype, the purest example of what all repeating fast radio bursts truly are, and the others are just harder to see in detail? Or is it the bizarre exception, a cosmic oddball that happens to be the loudest and most obvious, while the true population hides in quieter, more subtle forms? Its unique behavior is both a guiding light and a profound puzzle, a reminder that the first answer we find in the cosmos is rarely the whole story. The original repeater's chaotic outburst seemed to defy any sense of order, a cosmic tantrum without a schedule. Then came a discovery that was even more startling than the repetition itself. Some of these sources were not just repeating, they were keeping time. This is the ninth mystery, the stunning revelation of periodic activity. The most famous example is a repeater designated FRB 180916.J0158+65, discovered by the CHIME telescope in Canada. After months of careful monitoring, a pattern emerged from the noise. For roughly 4 days, this source would fire off bursts, sometimes many in an hour. Then, as if a switch was flipped, it would fall completely silent for about 12 days. After that quiet period, the activity would start again. The entire cycle repeated every 16.35 days with a precision that felt almost mechanical. This was not random chaos, this was a clockwork cataclysm. The immediate question was, what kind of cosmic clock could govern such immense sporadic violence? Two leading theories emerged, each painting a vivid picture of the source's environment. The first involves a wobble. Imagine a spinning neutron star, its beam of radiation sweeping across space like a lighthouse. If the star is not perfectly balanced, it can precess, meaning its rotational axis slowly wobbles in a circle over time, much like a spinning top winding down. This wobble could cause its deadly beam to point toward Earth only during a specific window in that cycle, creating the active period before sweeping away for the quiet interval. The second, and perhaps more compelling theory, involves a dance with a companion. Picture the fast radio burst source, likely a magnetar, locked in orbit with another massive object, perhaps a massive star or a black hole. As it orbits, there are phases where it moves behind a thick veil of material, like a dense stellar wind or an accretion disk flowing from the companion. For most of its orbit, this shroud blocks the radio bursts from reaching us. Only when the magnetar emerges into a clear line of sight, a window lasting a few days, can its screams reach our telescopes. This binary system model is particularly powerful because it explains not just the periodicity, but also the nature of the bursts themselves. The violent interaction with the companion's wind or gravitational pull could be providing the extra energy needed to trigger the outbursts, like stirring a pot until it boils over. The 16-day cycle is more than just a curious pattern. It is a direct window into the geometry and the relationships of these objects. It tells us we are not looking at an isolated monster, but at a system, a dynamic relationship where gravity and plasma choreograph some of the most powerful explosions in the universe. The silence between the bursts is just as informative as the flashes themselves, a scheduled quiet that speaks volumes about the hidden machinery at work. That cosmic clockwork hints at an ordered environment, but the bursts themselves carry a more chaotic signature in their very sound. Many repeating bursts as they unfold over a few milliseconds perform a strange spectral trick. If you could translate the radio signal directly into sound, it would not be a single, pure tone. Instead, you would hear a rapid series of chirps, each one starting at a higher pitch and sliding unmistakably downward, like someone running their finger down the keys of a piano or the falling glissando of a slide whistle. Astronomers call this the downward drifting burst, and it is one of the most distinctive and puzzling fingerprints in the fast radio burst catalog. This spectral drift is not random. The individual sub-pulses within a burst appear at progressively lower radio frequencies as time goes on. The first pulse might be at, say, 1,400 MHz, the next at 1,390, the next at 1,380, and so on, creating that characteristic downward swoop in the data. It is such a recognizable pattern that researchers have informally dubbed it the sad trombone effect. But what cosmic instrument could possibly produce such a mournful glissando? This drift is not a product of the long journey through intergalactic space, that is the dispersion measure we discussed earlier. This is something intrinsic to the burst itself, a clue written into the signal at its moment of creation. The leading explanation takes us back to the environment around a magnetar or a highly active neutron star. Imagine the star is surrounded by a dense, magnetized cloud of plasma, a chaotic soup of charged particles held in the grip of an immense magnetic field. When a starquake or magnetic reconnection event happens on the surface, it launches a shock wave or a blast of energy outward through this cloud. Think of this blast as a disturbance moving upward from the star's surface through layers of plasma that get less and less dense the farther out you go. Now, a fundamental property of plasma is that different radio frequencies are emitted at different densities. Higher frequency radio waves are produced in regions of higher plasma density, closer to the star. Lower frequencies are produced in thinner plasma, farther out. So, if the disturbance travels upward, it first triggers emission in the high-density, high-frequency region near the star. As it propagates outward, it then triggers emission in progressively lower density, lower frequency zones. From our distant vantage point, we see the high-frequency pulse first, followed by pulses from higher and higher altitudes, each at a lower frequency. It is like watching a flare ignite at the base of a tall structure and then seeing the fire climb upward, lighting different floors as it goes. The precise rate of the frequency drift gives astronomers a direct probe of this plasma environment. By measuring how quickly the pitch falls, they can estimate the magnetic field strength and the density gradient around the source. It is a remarkable piece of remote sensing, using a fleeting radio chirp to map the invisible layers of magnetized chaos surrounding one of the most violent objects in the universe. This sad trombone sound, then, is not just a curious artifact. It is the literal sound of an explosion climbing through a star's atmosphere, a sonogram of cosmic violence that lets us hear the structure of the storm. The sad trombone's falling pitch maps a single explosion, but some sources refuse to play just one note. They erupt into a frenzy, a storm of radio flashes that defies any sense of moderation. This is the mystery of the extremely high burst rate, moments when a fast radio burst source goes into a state of pure, chaotic overdrive. One of the most dramatic examples is a repeater designated FRB 2022-0912A. In just 2 months of observation, this single object fired off over 200 distinct bursts. It was not just active, it was hyperactive, producing brilliant millisecond flashes, sometimes mere minutes apart. Each burst was a colossal release of energy, and yet the source kept firing again and again, as if its power supply was bottomless. This hyperactive state tells us something critical about the central engine. It cannot be a simple, one-time explosion. The object must have a vast and stable reservoir of energy to draw upon, and a trigger mechanism that can be pulled over and over without destroying the system. Think of it not as a bomb, but as a capacitor, a cosmic battery that can discharge violently, recharge, and discharge again in rapid succession. The most likely culprit, once again, is a magnetar. Its energy reservoir is the unimaginable power bound up in its twisted magnetic field. A starquake might release one strand of that field, causing a single burst. But in a hyperactive state, it is as if the entire crust of the star is fracturing in a cascade of seismic events, or the magnetic field is undergoing continuous, violent reconnection, snapping and reforming like a bundle of over-tightened rubber bands. The sheer number of bursts tells us the engine is robust, it can survive its own fury. Yet this makes the contrast with quiet periods all the more baffling. The same source that can produce 200 bursts in 2 months can then fall silent for years. What is the trigger that flips the switch from quiescence to frenzy? For a magnetar in a binary system, it could be the close approach to its companion, where tidal forces or plowing through a dense stellar wind stirs the magnetic part to a boiling point. For an isolated magnetar, it might be the slow buildup of strain in its crust until a critical threshold is crossed, initiating an avalanche of starquakes. These violent episodes are like cosmic geysers, where pressure builds invisibly beneath the surface until it erupts in a spectacular, transient display. The switch between silence and storm remains one of the most urgent puzzles, because understanding that trigger means understanding what finally tips the scales in an environment where unimaginable forces are in a perpetual, tense standoff. A hyperactive burst storm unleashes the energy of stars, yet it screams in near total silence across the rest of the light spectrum. This is the 12th mystery, the confounding absence of counterparts. When an event radiates the power of a fast radio burst, physics insists it should not be a radio-only show. Such a colossal, sudden release of energy should set the entire electromagnetic spectrum ablaze, from low-energy radio waves up through visible light into the searing realms of X-rays and gamma rays. It should be a cosmic fireworks display visible in every color, except it almost never is. For the vast majority of bursts from distant galaxies, the brilliant radio flash is all we get. The aftermath is a profound and puzzling quiet. Following a fast radio burst detection, an urgent alert races to observatories worldwide. Space telescopes like Swift and Chandra, designed to catch the high-energy glow of cosmic explosions, pivot to stare at the coordinates. Giant optical eyes like Hubble and its successors take deep, careful images. They are searching for a fading afterglow of visible light, a persistent X-ray source, or even a faint gamma-ray whisper. Almost always they find nothing. The sky remains dark at all other wavelengths. This consistent emptiness is a massive constraint, a boundary that any successful theory must explain. It tells us the engine is astonishingly efficient at producing radio waves, but incredibly inefficient, or perhaps deliberately focused, at producing anything else. The rare exceptions are what make the rules so baffling. Our own galactic Magnetars outburst in 2020 came with both radio and X-rays, proving a connection exists. And for the famous repeater FRB 121102, astronomers did catch a single, simultaneous flicker of X-rays during one radio burst. These hints are tantalizing, but they are flashes in a void of non-detection. So why the radio silence elsewhere? One possibility is that we are simply not looking fast enough. The multi-wavelength flash might be even briefer than the radio burst itself, lasting only microseconds, and our telescopes are too slow to catch it. Another, more intriguing idea is that the environment around the source acts as a filter. Imagine the burst originates deep within a thick, magnetized nebula or a powerful stellar wind. Radio waves can escape this shroud relatively easily, but higher energy light like X-rays and gamma rays are absorbed or scattered, converted into lower energy radiation before they can break free. It is like hearing the deep thump of music from a fortified nightclub, while the strobe lights inside are completely hidden by the walls. Alternatively, the mechanism itself might be inherently clean. A process like a coherent maser emission in radio that does not involve the chaotic thermal processes that typically produce broad-spectrum light. Every empty search narrows the path forward, forcing theorists to build engines that are not just powerful, but also strangely quiet, broadcasting their cataclysms on only one very specific cosmic channel. The missing counterparts are not a failure of observation. They are a loud message about the unique and hidden physics of these events, a message written in the light that did not arrive. That profound silence across most of the spectrum forces us to listen even more carefully to the one signal we do receive, the radio flash itself. Within that fleeting burst of static, hidden in the very orientation of its radio waves, lies another layer of encoded information. This is the 13th mystery, the story told by Faraday rotation, a subtle twisting of the signal that maps the invisible magnetic fields it has traveled through. To understand it, picture a radio wave as a vibration, a tiny electric field oscillating in a specific direction, like a rope being shaken up and down. This orientation is called its polarization. When such a polarized wave travels through a region filled with both free electrons and a magnetic field, something remarkable happens. The magnetic field causes the wave's plane of polarization to slowly rotate, like a compass needle turning as it moves through different terrain. The more electrons and the stronger the magnetic field along the path, the greater the twist. This effect is Faraday rotation, and it is a cosmic gift. It means every fast radio burst carries within it a magnetic fingerprint, a record of every magnetized plasma cloud it has passed through on its billion-year journey to us. By measuring how much the polarization plane has been twisted, astronomers can probe the magnetic environment both in the host galaxy and in the vast intergalactic medium between galaxies. Most bursts show some Faraday rotation, confirming that magnetic fields are woven throughout the cosmos, but one source stands out for its extreme reading. The original repeater, FRB 121102, exhibits a Faraday rotation so massive it is off the charts compared to any other astronomical source. The signal is not just slightly twisted, it is corkscrewed. Decoding this extreme value points to an environment of almost unimaginable magnetic fury. To produce such a rotation, the burst must have traveled through an incredibly dense, intensely magnetized plasma right at its source. This is not the weak, diffuse field of interstellar space. This is the crushing magnetic field at the heart of a cosmic maelstrom. Two leading scenarios could create such a zone. The first places the repeater in the immediate vicinity of a supermassive black hole, perhaps within its swirling accretion disk or the powerful jets it launches. Here, plasma is superheated and magnetic fields are wound to breaking point by the black hole's spin. The second, and currently favored, scenario places it inside a persistent, magnetized nebula powered by a young, hyperactive magnetar. This nebula, glowing faintly in radio waves as we see, would be a turbulent soup of particles and magnetic fields ejected from the star, a perfect environment to impart that severe twist to any signal escaping it. The Faraday rotation is a quiet, profound clue. It tells us that for at least some of these bursts, the engine is not just powerful, it is sitting in the middle of a magnetic hurricane, a storm so intense it leaves its mark on every single scream that escapes. The profound magnetic twist of Faraday rotation is a clue etched into the signal by its environment, but the journey itself imprints an even broader signature. This leads us to a pivotal shift in perspective. Fast radio bursts are not merely cosmic mysteries to be solved, they are becoming some of our most powerful tools for mapping the universe itself. Each burst acts as a brilliant, fleeting lighthouse, and its beam illuminates the darkest, most diffuse corners of the cosmos as it travels toward us. The key is in that dispersion measure, the smear caused by the thin plasma between galaxies. For decades, cosmologists have faced a perplexing accounting problem called the missing baryon problem. Baryons are the ordinary matter that makes up stars, planets, and us. When we tally all the normal matter we can see in galaxies and galaxy clusters, it accounts for only about half of what the Big Bang's recipe predicts should exist in the present-day universe. The rest, a staggering amount of material, is missing. The leading theory is that these missing baryons are hiding in the warm, hot intergalactic medium, a tenuous web of ionized gas filaments stretching between galaxies. This gas is so hot and diffuse it emits almost no light of its own, making it nearly invisible to traditional telescopes. This is where fast radio bursts become revolutionary probes. As a burst's radio waves traverse this cosmic web, they interact with every free electron in their path. The greater the dispersion measure, the more total electrons the signal has encountered. By using the precise distance to a burst's host galaxy, obtained from its redshift, astronomers can calculate exactly how many electrons should be spread along that line of sight if the theoretical models of the cosmic web are correct. The dispersion measure provides the actual, observed count. Early results are astonishingly promising. The numbers match. The dispersion from distant bursts aligns almost perfectly with predictions for the amount of material in the warm, hot intergalactic medium. It seems we are finally detecting the universe's missing normal matter, not by seeing it glow, but by seeing how it delays and smears a cosmic flash passing through it. Each localized fast radio burst gives us a single, precise core sample through the cosmic web. As we collect more of these samples from different directions and distances, we can begin to build a three-dimensional map of this invisible structure, tracing the distribution of the universe's hidden backbone. The very signal that poses such a profound mystery about its origin is in its journey solving one of cosmology's oldest puzzles, turning a question mark into a measuring stick for the cosmos. Mapping the universe's missing matter is a profound application, but it requires catching these fleeting flashes in the first place. For years, that was the bottleneck. Traditional radio telescopes are like looking through a drinking straw, covering a tiny patch of sky at a time, making the chance of catching a millisecond burst from any direction a cosmic lottery. Then came a quiet revolution in a Canadian valley. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, was not even built to hunt fast radio bursts. Its primary mission was to measure the expansion history of the universe by mapping the distribution of neutral hydrogen. To do that, it needed an unprecedented combination of traits, a massive collecting area, and an incredibly wide field of view. CHIME has no moving dishes. Instead, it consists of 4 giant, stationary half-pipe cylinders, each 100 meters long, lined with over 1,000 antennas. It stares fixedly at the sky as the Earth rotates, scanning a strip of the heavens 180 degrees wide every single day. This design made it, by accident, the perfect fast radio burst interceptor. While other telescopes might peer intently at one star, CHIME watches the entire sky parade past. When it began operations in 2018, the floodgates opened. CHIME went from detecting a handful of bursts per year to discovering hundreds, then thousands. It transformed the field overnight from studying rare, individual curiosities to analyzing populations and statistics. We were no longer just collecting exotic stamps, we were taking a census of the cosmos. CHIME torrent of data yielded immediate breakthroughs. It found new repeaters at an astonishing rate, confirming that repeating sources were not a fluke but a common, perhaps dominant class. Most spectacularly, it was CHIME that discovered the first fast radio burst with a clear, predictable period, the 16-day cycle of FRB 180916. That single detection from its relentless all-sky monitoring proved these events could be clockwork, opening the door to the binary system and precession models that now define our thinking. CHIME did not just find more bursts, it found new kinds of bursts, revealing the true diversity and hidden order within the chaos. Its wide, unblinking gaze turned a trickle of data into a river, and in that river, we began to see the true shape of the mystery for the very first time. But even among CHIME's flood of discoveries, one burst stands apart, not for its pattern, but for its raw, terrifying power. This is the story of fast radio burst 2022-0610A, the record breaker. Detected in June of 2022, this was not a repeater. It was a single, catastrophic blast, a cosmic scream of such ferocity that it redefined the upper limits of what we thought was possible. The numbers are staggering. In less than a millisecond, it released an amount of radio energy equivalent to our sun's total output over 30 long years. All of that power focused into a flash briefer than the blink of an eye. Its dispersion measure, that cosmic odometer, was correspondingly immense. The signal was so smeared by its journey through intergalactic electrons that astronomers calculated it must have traveled for nearly 8 billion years before reaching us. This places its origin at a time when the universe itself was only about 5 billion years old, still in its relative adolescence, a period of intense star formation and galactic chaos. The burst was so powerful that its path appears to have taken it directly through a cluster of galaxies, a massive knot in the cosmic web, which may have further lensed and amplified the signal on its way. The implications are profound. If such an unthinkably energetic event could occur in the universe's younger, denser days, it tells us that the conditions to create these monsters were not only present but perhaps more common in that turbulent era. The engine behind this burst must have been a product of its time, possibly involving the collision of supremely dense objects formed from the universe's first generations of massive stars, or a magnetar born with magnetic fields even more extreme than those we see in our modern, quieter cosmos. The hunt for its host galaxy continues, a painstaking search through the region of sky flagged by CHIME. Finding that faint, distant smudge of stars is the crucial next step. Did this titanic flash come from a massive galaxy cluster, a fitting birthplace for such violence? Or did it erupt from a modest dwarf galaxy, proving that even the smallest cosmic neighborhoods can produce the largest explosions? Until we find its home, FRB 2022-0610 remains a solitary monument to a universe capable of sudden, breathtaking violence on a scale that still, even now, defies our full comprehension. That record-breaking blast from the early universe is the ultimate one-off, a final, brilliant scream. But what cosmic catastrophe could produce such a singular, devastating flash? For the non-repeating fast radio bursts, the leading theories are all stories of annihilation, where the source is utterly destroyed in the process. The first and perhaps most elegant scenario is the merger of two neutron stars. Picture these city-sized remnants of dead stars, each more massive than our Sun, locked in a final, decaying orbit. As they spiral inward over millennia, they rip at each other's fabric with immense tidal forces, until finally, in a last millisecond, they collide. The resulting kilonova is known to produce gravitational waves and a short gamma-ray burst, but some models suggest that in the chaotic magnetic maelstrom of the merger, a colossal, one-time blast of coherent radio waves could also be launched just before the final impact. It is a death cry in radio, a final signal before the two stars become one. The appeal of this model is its connection to other known phenomena, but it faces a major hurdle. We have now detected several neutron star mergers through their gravitational waves and gamma rays, like the famous event GW 170817. None of them have been accompanied by a fast radio burst bright enough for us to detect from across the universe. If mergers do produce them, the radio beam must be exceptionally narrow, or the process far less efficient than we think. Another cataclysmic possibility is the collapse of a supermassive neutron star into a black hole. Some neutron stars may be born with, or accrete, so much mass that they balance on the very edge of stability, right at the Tolman-Oppenheimer-Volkoff limit. For a time, the immense pressure of quantum forces holds the star up against the crushing weight of its own gravity. But if just a little more matter falls onto it, or if it slowly loses spin, that delicate balance can shatter in an instant. The entire star, perhaps 25 kilometers across, would implode in a flash as its core vanishes into a black hole. Theorists propose that during this sudden transition, the magnetic field lines anchored to the star's surface are snapped and reconfigured with unimaginable violence, potentially powering a single, tremendous radio blast as the star's magnetic soul is extinguished forever. This model is compelling because it naturally explains why we never see a repeat. The object is gone, yet it too struggles with the lack of consistent counterparts. Such a collapse should also produce a burst of neutrinos and possibly a weak gamma-ray signal, none of which have been definitively linked to a fast radio burst. A third, dramatic model involves a star wandering too close to a supermassive black hole. In a tidal disruption event, the black hole's gravity pulls the star apart into a long, spiraling stream of gas. As this material falls inward and heats up, it creates a brilliant flare across the electromagnetic spectrum. Some simulations suggest that within the chaotic plasma of this accretion flow, powerful magnetic shocks could generate a brief, intense pulse of radio waves. This model elegantly ties fast radio bursts to another known class of transient event. However, observed tidal disruption events produce bright, long-lasting optical and X-ray emission, not the isolated radio flash we see. For a fast radio burst to be the main signal, the event would have to be somehow shrouded or the radio production uniquely efficient, which remains speculative. The fundamental challenge linking all these cataclysmic models is the deafening silence that often follows. If a neutron-star merger or a stellar collapse happens in a galaxy far away, our gravitational wave detectors like LIGO and Virgo should, in principle, feel the ripples in spacetime. Our gamma-ray satellites should catch the high-energy flash. Yet for the vast majority of non-repeating fast radio bursts, no such counterpart is found. This silence could mean we are looking at the wrong angle, that the gamma rays are beamed in a different direction than the radio waves. Or, more intriguingly, it could mean these one-off bursts are not so cataclysmic after all. Perhaps they are merely the loudest scream from a repeater on a 1,000-year cycle, or the signature of a Magnetar starquake so violent it temporarily exhausts its magnetic field, entering a long hibernation. The destruction of the source is a clean, satisfying explanation, but the universe has a habit of favoring stories of survival and repetition over finality. The search for that confirming flash of light or ripple in spacetime continues, a hunt for the echo that would prove some of the universe's most brilliant flashes are also its final goodbyes. Yet the search for cataclysmic counterparts often comes up empty, forcing a compelling alternative. Perhaps the most shocking truth is that a fast radio burst does not require the death of a star at all. The source might survive the blast perfectly intact, firing again and again from a reservoir of energy that is vast but not infinite. This leads us into theories of non-cataclysmic origins, where the engine is not destroyed but merely agitated, like a bell that rings violently but remains unbroken. The most natural suspects are, once again, neutron stars, but in less apocalyptic roles. Consider the humble pulsar, a spinning neutron star that emits a steady lighthouse beam of radio waves. Occasionally, some pulsars produce what are called giant pulses, bursts of radio emission millions of times brighter than their normal pulse. These are thought to come from specific, stormy regions in the star's magnetosphere. Could a fast radio burst simply be a giant pulse from an extremely powerful, distant pulsar? The energy scales are challenging, but perhaps a young, rapidly spinning pulsar with a colossal magnetic field, a magnetar in all but name, could manage it. This model neatly explains repeaters as the pulsar spins on, capable of producing more giant pulses whenever conditions are right in its turbulent atmosphere. Another non-destructive idea draws from our own solar system. Imagine a neutron star with a remnant asteroid belt or a cloud of comets left over from the supernova that birthed it. If a large asteroid, perhaps a few kilometers across, were to plunge into the neutron star's atmosphere, the impact would release a tremendous flash of energy as the rock is vaporized by intense pressures and magnetic forces. This would be a one-time event for that particular asteroid, but with a whole belt of debris, the star could experience multiple impacts over time, creating a repeater with irregular intervals. The energy from such an impact is theoretically sufficient, and it provides a natural way to explain why some bursts seem so sporadic. Yet, it struggles to account for the highly structured, downward drifting bursts or the precise periodicity seen in some sources. An asteroid strike is a messy, chaotic explosion, not likely to produce the clean, frequency-drifting chirps we observe. A more elegant and promising non-cataclysmic model is known as the cosmic comb. Picture a fast-spinning pulsar with a powerful, steady wind of particles flowing outward. Now, imagine this pulsar is plowing through a dense, static cloud of plasma, perhaps the nebula from its own birth. As the pulsar spins, its magnetic field acts like a rotating rake or a comb, periodically sweeping through this cloud. Each time the magnetic field lines snap through the dense plasma, they can trigger a shock wave that accelerates particles, producing a brilliant, brief burst of coherent radio emission. This model beautifully accounts for repeaters with periodicity as the comb sweeps at the pulsar's rotation rate. It can also explain complex burst structures if the cloud is lumpy and uneven. The persistent radio source seen around the original repeater could be the glowing nebula itself, the very cloud being combed by the central engine. This idea turns the fast radio burst from a singular explosion into a regular interaction, a product of the relationship between a spinning magnet and its environment. Evaluating these models against the evidence creates a fascinating puzzle. For the highly active, seemingly chaotic repeaters like the original, models involving a Magnetars crustquakes or the cosmic comb interacting with a turbulent nebula fit well. They provide a durable engine and a way to explain the persistent radio glow. For the repeaters with clockwork precision, the cosmic comb or a precessing magnetar in a binary system are strong contenders as they introduce a natural geometric clock. The asteroid impact model, while creative, seems better suited for explaining occasional, irregular bursts rather than the complex, structured, and sometimes frantic activity we see. What becomes clear is that non-cataclysmic models are not just alternatives, they are increasingly necessary. They explain why we see the same spot in the sky light up over years, and why some sources can erupt hundreds of times without apparent exhaustion. The universe may be ringing neutron stars like bells, and we are just hearing the loudest, most resonant chimes from across the cosmic void. The non-cataclysmic models paint a picture of durable engines, but their signals can be warped by the very fabric of space on the way to us. This brings us to a fascinating and still hypothetical frontier, the potential for gravitational lensing. Imagine a fast radio burst traveling for billions of years on a straight path toward Earth. Now picture its final approach, where its path skirts a massive galaxy cluster or even a single, dense dark matter halo. According to Einstein's theory, mass curves spacetime. That curvature acts like a cosmic lens, bending the path of any radiation, including radio waves. For a fast radio burst, this lensing could manifest in several eerie ways. The signal could be magnified, making a faint burst appear startlingly bright in our telescopes. More intriguingly, the single burst could be split into multiple images, taking slightly different paths around the lens. We would then detect the same millisecond flash arriving at 2 or 3 distinct times, separated by milliseconds, days, or even weeks. This would create a perfect echo, a ghostly duplication of the event. The delay between these copies is not random noise, it is a precise measurement. By analyzing the time difference, astronomers could directly map the mass distribution of the invisible lensing object, whether it is a galaxy, a black hole, or a clump of dark matter. This offers a potentially revolutionary tool. Most of the universe's matter is dark, not emitting any light. A lensed fast radio burst could act as a backlight, revealing the shape and density of these hidden structures simply by how they delay the signal. Furthermore, because the time delay depends on both the mass of the lens and the geometry of the entire path from the burst to us, a strongly lensed burst could provide an independent, precise measurement of the expansion rate of the universe, the Hubble constant. This is one of the most significant tensions in modern cosmology, with different methods yielding disagreeing values. A lensed fast radio burst could be a new, clean ruler to help settle the debate. The tantalizing possibility is that we may have already recorded a lensed burst without realizing it. Some events with complex, multi-peaked structures or unexplained echoes in the data could be candidates. But so far, despite clear predictions and active searches, a conclusively identified gravitationally lensed fast radio burst remains elusive. Its discovery would be a monumental event, transforming these flashes from mere cosmic mysteries into precision instruments for probing the universe's darkest secrets. The gravitational lensing of a burst would reveal the universe's large-scale architecture, but even without such dramatic warping, the signal itself can shimmer and dance. This scintillation is not a flaw in the transmission, but a message about the turbulent plasma the burst has traversed. Picture a fast radio burst signal as a steady, coherent beam of radio light. On its long journey, it inevitably passes through clouds of ionized gas, clouds that are not smooth and uniform, but churning with density fluctuations like heat haze rising from asphalt. As the radio waves pass through these turbulent plasma screens, the denser patches slow the light down slightly more than the thinner patches. This creates tiny differences in the travel time across the wavefront, causing the signal to interfere with itself. From our perspective, the single, steady point of light begins to twinkle, its intensity flickering rapidly in time and across different radio frequencies. It is the exact same phenomenon that makes stars appear to twinkle in our night sky as their light passes through Earth's turbulent atmosphere. For a fast radio burst, this scintillation is a cosmic gift. By carefully analyzing the intricate pattern of this twinkling, astronomers can perform a remarkable feat of remote sensing. The scale of the scintillation pattern tells us the size of the turbulent eddies in the plasma cloud. The rate at which the pattern changes tells us how fast that cloud is moving relative to our line of sight. It is like studying the intricate, moving shadows cast on a wall by a frosted glass window, and from those shadows deducing the exact texture of the glass and the motion of the light source behind it. Most powerfully, scintillation can reveal if the plasma screen is close to us, within our Milky Way, or out in the vast intergalactic medium. A burst that scintillates strongly at low radio frequencies but becomes steady at higher frequencies is telling us it passed through a very nearby turbulent screen, like the ionized gas in our galaxy's spiral arms. If the scintillation pattern is seen across a wide band of frequencies, it suggests the plasma is much closer to the burst source itself, perhaps in its host galaxy or even in the immediate nebula surrounding it. In one extraordinary case, astronomers observed the scintillation pattern of a repeating fast radio burst change over several months. This was not random noise, it was a direct measurement of relative motion. It meant the turbulent plasma cloud causing the twinkle, the burst source itself, and our solar system were all moving relative to each other. By untangling these motions, they could estimate the speed of the source through its own environment, painting a dynamic portrait of a hyperactive magnetar plowing through the debris of its birth. Each flicker in the signal, then, is a micromap of the universe's invisible, churning seas of plasma, allowing us to trace structures far too faint and small to see by any other means. The scintillating whispers from distant galaxies are clues we must decode from billions of light years away. But the ultimate prize for astronomers would be to catch a fast radio burst erupting right here in our own cosmic neighborhood. The search for a Milky Way fast radio burst is a hunt for a homegrown monster, an event that would transform our understanding by letting us study one up close. For years, it was a tantalizing possibility. If magnetars were truly the engines as suspected, we have several dozen of these magnetic monsters known within our galaxy. Statistically, one should flare with a radio burst bright enough for our telescopes to see. The anticipation built with every new magnetar outburst, a waiting game for the right kind of explosion. Then, in April of 2020, the moment arrived, but with a puzzling twist. A galactic magnetar named SGR 1935+2154, already known for its occasional X-ray grumbles, suddenly erupted. This time, radio telescopes caught a millisecond blast of radio waves alongside the high-energy flash. The astronomy community erupted with excitement. We had finally seen a fast radio burst, or something very much like one, from a confirmed source within our own galaxy. The connection between magnetars and these signals was proven. Yet, the celebration was tempered by a stark fact. The radio burst from our galactic magnetar, while powerful, was thousands of times fainter than the faintest extragalactic fast radio bursts we routinely detect. It was a whisper compared to the cosmic shouts from distant galaxies. This left a profound and lingering question. Will we ever witness a full-strength, cosmological-style fast radio burst from inside the Milky Way? Such an event would be a scientific bonanza of unimaginable scale. Imagine the detail. We could point every telescope we have across every wavelength at the known source within moments. We could search for neutrinos, for gravitational waves, for any faint optical afterglow with a precision impossible for a source billions of light-years distant. We could map the magnetic field around it in real time, watch the aftermath of the explosion for days or weeks, and potentially even identify the progenitor system like a binary companion in exquisite detail. It would be like studying a volcano from a laboratory next door instead of through a telescope on another continent. The energy requirements, however, are daunting. For a magnetar in our galaxy to produce a burst as bright as those from cosmic distances, it would need to undergo a starquake or magnetic reconnection event of almost unimaginable violence, perhaps orders of magnitude more powerful than anything we have recorded. Some theorists suggest such an event could be a once-in-a-millennium occurrence for any given magnetar. Others wonder if the truly colossal bursts require special conditions our local magnetars lack, like the dense nebula of a recent supernova remnant or the intense gravitational stirring of a binary partner. The detection of a true galactic fast radio burst would not just be a lucky break. It would be a direct message, a Rosetta Stone delivered to our doorstep, allowing us to translate the cryptic signals from across the universe with a clarity we can only dream of today. The telescopes are listening, trained on our own magnetic monsters, waiting for one of them to scream. The galactic magnetar's faint whisper suggests its youth, but to trace these signals back to their violent birth, we must look for the echoes of stellar death. The link between fast radio bursts and supernova explosions is a compelling and messy chapter in the story. When a massive star, many times heavier than our Sun, reaches the end of its life, it does not fade quietly. Its core collapses in a cataclysm known as a supernova, an explosion so brilliant it can outshine an entire galaxy for weeks. What remains is a city-sized, hyper-dense cinder, a neutron star. If that star is born spinning furiously with a magnetic field wound to impossible tightness, it becomes a magnetar. The logic is beautifully simple. Young, active magnetars, still crackling with the energy of their violent formation and often embedded in the expanding debris of their own birth, are perfect candidates to produce the repeating, chaotic bursts we see. This model fits neatly with the environments of some famous repeaters. The original FRB 121102 sits in a dwarf galaxy ablaze with star formation and is surrounded by that persistent radio nebula, which many astronomers interpret as the glowing remnant of the supernova that created it. It is a picture of cosmic adolescence, a newborn monster screaming inside its own crib of stellar wreckage. The theory suggests we should find fast radio bursts primarily in galaxies that are stellar nurseries, places where massive stars are born, live fast, and die young in supernova, constantly seeding the galaxy with fresh magnetars. And indeed, many localized bursts come from such active, star-forming galaxies. But the universe, as always, complicates the narrative. Not all fast radio burst hosts fit this youthful profile. We have found them in massive, quiet galaxies where the era of rampant star formation ended billions of years ago. In these serene, elderly neighborhoods, the massive stars that make magnetars through core collapse supernova have been dead for eons. So what is producing the bursts there? This forces us to consider a slower, older pathway. Perhaps the engine is a neutron star that has wandered for billions of years, a relic from the galaxy's violent youth, and has only now been triggered. How could an old star reactivate? One possibility is through accretion. If this ancient neutron star has a binary companion, a normal star that has aged into a red giant, it might begin to siphon material from its partner. This incoming matter could spin the neutron star back up and reignite its magnetic field, essentially rebirthing it as a magnetar-like object capable of powerful outbursts. Another possibility is a delayed collapse. Some neutron stars might be born just below the critical mass to become a black hole. Over millennia, they could slowly accrete tiny amounts of interstellar dust or be nudged by a collision with another star until they finally cross that threshold and collapse, producing a one-time cataclysmic burst. The search for supernova remnants around localized bursts is a direct test. For bursts in young galaxies, astronomers scour the precise location for the telltale, expanding shell of gas that marks a recent supernova, perhaps only decades or centuries old. Finding one would be a smoking gun. For bursts in old galaxies, the absence of a fresh remnant is just as telling, pointing to an older, reactivated engine. The evidence so far is mixed, a sign that both pathways might be real. The universe may create its brilliant radio flashes in two ways: in the fiery aftermath of a star's death, and in the slow-burning reawakening of a stellar ghost from a bygone era. That slow-burning reawakening in an old galaxy might be sparked by a cosmic partnership. The clockwork precision of a 16-day cycle points directly to a dance of immense gravity, a binary system where a fast radio burst source is locked in orbit with a companion. This is not a solitary monster, but a relationship, and the dynamics of that relationship could be the key to both the timing and the terrifying power of the burst. The simplest model involves a magnetar paired with a massive, hot star. As the magnetar orbits, it periodically plunges through the thick stellar wind flowing from its giant partner. Think of it like a speedboat cutting through a dense fog, creating a bow shock. Each time the magnetar enters this dense wind, the violent interaction between its own immense magnetic field and the incoming plasma could trigger a storm of reconnection events, powering a series of fast radio bursts. The active window corresponds to the part of the orbit where the magnetar is deepest in the wind, and the quiet period is when it emerges into clearer space. This elegantly explains why we see bursts only during specific phases, but the companion could be even more extreme. Imagine a binary system of two neutron stars spiraling ever closer. In the final millennia before they merge, their magnetic fields could interact chaotically, with tidal forces stressing their crusts to the breaking point. Each close pass could trigger a series of starquakes on one or both stars, producing a fast radio burst. The orbital period would dictate the timing of these violent close encounters, creating a predictable, repeating pattern of activity. This model is particularly thrilling because it links the repeating bursts we see today to the final cataclysm of a merger we might detect tomorrow. Perhaps the most dramatic scenario involves a black hole companion. Here, the magnetar orbits not a star, but the ultimate cosmic sinkhole. As it swings through its orbit, it might pass through the black hole's accretion disk, a swirling maelstrom of superheated gas. Plowing through this dense material would be like running into a wall of plasma, an interaction of unbelievable violence that could easily power a colossal radio blast. Alternatively, the mere gravitational tug of the black hole on each close approach could squeeze the magnetar, triggering colossal starquakes in its crust. In all these models, the orbit provides the clock. The 16.35-day period of the famous repeater is not just a number, it is a direct measurement of the system's scale. From that period, using Kepler's laws of motion, astronomers can estimate the separation between the two objects. For a system involving a magnetar and a massive star, that distance would be on the order of tens of millions of kilometers, about the distance from Mercury to the Sun. This creates a specific environment, one where stellar winds and gravitational tides are powerful enough to matter. The binary model does more than explain periodicity, it also solves the energy problem. A lone magnetar must draw all its burst energy from its own internal reservoir of magnetic stress, which could eventually be exhausted. But in a binary system, the companion provides a continuous external source. Accretion, the steady drizzle of stolen material from the companion star onto the magnetar, can spin it up, feed its magnetic field, and constantly recharge the battery. The gravitational tides can continuously stress the crust, like squeezing a stress ball over and over. The binary partner is not just a timekeeper, it is the engine's fuel pump and trigger mechanism combined. Is the 16-day cycle definitive proof of a binary origin? It is the strongest evidence we have, a fingerprint of orbital motion that is incredibly difficult to explain with a single wobbling object. A precessing neutron star could have a similar period, but matching the precise on-off windows of activity is a taller order for precession alone. The binary model naturally creates those sharp transitions like an eclipse as the source moves into and out of a shroud of wind or disk material. Every new repeater discovered with a stable period adds weight to this idea, suggesting that for at least a significant fraction of these sources, the brilliant flash in the darkness is not a solo performance, but a deadly duet written in the laws of gravity. That deadly duet plays out across the universe, but we can only hear the notes our telescopes are tuned to receive. Most of the fast radio bursts we have catalogued sing in a specific range, around 1 to 2 gigahertz, the pitch of common satellite and cell phone signals. This is not necessarily where they are loudest, it is simply where our most sensitive radio telescopes have traditionally listened. But when astronomers pointed instruments designed for lower frequencies, below 400 MHz, toward the same cosmic sirens, they were met with a puzzling silence. This is the mystery of the missing low-frequency bursts, a gap in the chorus that speaks volumes about the journey and the source. The expectation was simple. If a cataclysm produces a brilliant flash of radio waves, it should produce a broad spectrum, like an explosion creating both a deep boom and a high crackle. Yet for most fast radio bursts, the deep boom is conspicuously absent. One compelling reason lies in the scattering effect of the interstellar and intergalactic medium. Think of space not as a perfect vacuum, but as filled with a tenuous, turbulent fog of ionized gas. As a radio signal travels through this fog, the lower frequency waves, with their longer wavelengths, are much more easily deflected and delayed by the tiny density fluctuations. It is like how red light scatters less in our atmosphere than blue light, but for radio waves the effect is reversed. The lowest frequency waves get knocked around the most. Over billions of light years, this scattering can smear a sharp millisecond burst into a faint, washed-out hiss that lasts for seconds or even minutes, blending it into the background noise and making it impossible to distinguish as a distinct event. The burst might be there, but it is stretched so thin we cannot recognize it. Another possibility is absorption at the source. Imagine the fast radio burst engine is embedded in a dense, energetic nebula, like the persistent glow around the original repeater. This nebula could be so thick with hot plasma that it acts like a cosmic fog machine for its own signal. Low-frequency radio waves are particularly good at exciting electrons in this plasma, and in doing so, they can be absorbed, their energy converted to heat before it ever escapes the local environment. Only the higher frequency waves make it out. It is as if the source is screaming into a thick pillow, and only the highest pitched parts of the scream penetrate through. A third, more fundamental idea is that the emission mechanism itself simply does not produce strong low-frequency waves. The process that generates the coherent radio flash, perhaps a shock wave moving through a magnetized plasma or a magnetic reconnection event, might be intrinsically tuned, like a musical instrument that physically cannot produce notes below a certain pitch. The physics of these extreme environments might favor the generation of higher frequency radiation. To solve this puzzle, astronomers have deployed a specialized instrument, the Low Frequency Array or LOFAR, based primarily in the Netherlands. LOFAR is not a traditional dish telescope. It is a vast network of thousands of simple antennas spread across Europe, designed to catch the faintest whispers of the universe at frequencies as low as 10 MHz. Its strategy is twofold. First, it stares at the positions of known repeating fast radio bursts, hoping to catch a low-frequency counterpart to a high-frequency burst detected by other telescopes. Second, it scans the sky on its own, searching for bursts that originate entirely in this low-frequency realm. The results have been intriguing but sparse. LOFAR has detected a handful of extremely scattered, long-duration events that might be fast radio bursts viewed through the thickest cosmic fog, their sharp features completely blurred. It has also seen a few faint, low-frequency pulses from known repeating sources, but they are vastly weaker than their higher-frequency counterparts. Each non-detection is a clue, ruling out certain models and tightening the constraints on others. The hunt for the deep notes of the cosmic symphony continues because finding them would not just fill a gap in our data, it would reveal the true voice of the explosion, telling us precisely what lies between us and the source and what kind of instrument is playing this violent, universal song. Just as the deep notes of the cosmic symphony seem to fade away, the highest pitches are also strangely missing. While telescopes have hunted across the radio dial, there is a conspicuous silence at frequencies above about 8 GHz. This is the mystery of the high-frequency cutoff, a spectral wall that seems to block these bursts from reaching the highest registers of the radio band. It is as if the universe's most powerful radio transmitter is fundamentally incapable of producing a true screech, only a shout. The immediate question is whether this silence is a trick of our technology or a profound clue about the burst engine itself. Our most sensitive radio telescopes, like CHIME or ASKAP, are optimized for the sweet spot between 1 and 2 GHz, where celestial signals are strong and terrestrial interference is manageable. Few instruments are dedicated to continuously scanning the skies at frequencies above 8 GHz with the same wide-field millisecond precision. So, one possibility is simply that we have not been looking in the right place with the right tools. Bursts at those high frequencies might be intrinsically rarer or fainter, slipping through our observational nets. But if we assume our searches are sufficient, then the lack of detection points to something fundamental in the physics. The emission mechanism for fast radio bursts is thought to be coherent, meaning the radio waves are emitted in lockstep like a laser, rather than the chaotic thermal glow of a hot object. This coherence is what gives them their staggering brightness, but coherent processes often have natural frequency limits. One leading model involves radiation from charged particles gyrating wildly along magnetic field lines, a process called synchrotron maser emission. In the intense magnetic field near a magnetar, there is a theoretical maximum frequency this process can produce, a ceiling set by the strength of the field and the energy of the particles. Above that ceiling, the process simply cannot operate efficiently. Another possibility is absorption, but this time much closer to home. Our own Milky Way galaxy is filled with a thin haze of ionized gas. At very high radio frequencies, this interstellar medium can become opaque, absorbing signals before they even reach our telescopes. However, this effect is patchy and depends on the direction in the sky, while the lack of high-frequency bursts seems universal. More compelling is the idea of absorption at the source. If the burst is generated deep within a super-dense, magnetized plasma, that very plasma could act as a high-frequency filter, soaking up the highest energy radio photons before they escape. The spectral window we do see, from a few hundred megahertz to a few gigahertz, might be the only clean escape route for the signal, the one narrow band of radio light that can punch through the chaos surrounding the central engine. Pinpointing this cutoff frequency is not just a technical detail, it is a direct probe of the conditions in the heart of the explosion. If we can definitively measure a sharp high-frequency edge, it would give us a precise number to plug into our models, telling us the magnetic field strength or the plasma density with unprecedented accuracy. It would be like hearing a note cut off abruptly and knowing exactly how thick the wall is that stopped it. The hunt for these missing high notes continues, with newer telescopes pushing their capabilities upward. Each non-detection narrows the possibilities, quietly telling us that the universe's most brilliant flashes are not just powerful, but also strangely specific, broadcasting their secrets on a precise and limited band, a spectral fingerprint of the hidden storm. That spectral fingerprint points to a fundamental and bizarre truth about the burst engine itself. The extreme, almost impossible brightness of a fast radio burst cannot be explained by normal starlight. If it were just a hot object glowing, like the sun or a supernova, its radio signal would fade into undetectable noise long before it crossed billions of light years. The fact that we can hear these whispers from the edge of the observable universe means they are not just bright, they are unnaturally, artificially brilliant. This demands a special kind of physics called coherent emission. To understand coherence, think of a crowd. Incoherent emission is like a stadium full of people all talking at once. The sound is a chaotic roar, powerful but diffuse, fading quickly with distance. Coherent emission is that same crowd chanting in perfect, rhythmic unison. The combined sound becomes a focused beam, carrying much farther with stunning clarity. Most light in the universe, from stars to nebulae, is incoherent thermal radiation, the random jostling of hot particles. A fast radio burst is the cosmic equivalent of a laser beam or a precisely tuned radio transmitter. Its trillions of radio wave photons are all marching in lockstep, their waves perfectly aligned, amplifying each other to create that piercingly bright flash. The monumental challenge is this: what natural process in the cosmos can possibly organize trillions of charged particles, likely in a seething, chaotic plasma, to act as a single gargantuan antenna? On Earth, we achieve coherence with carefully engineered technology, like the klystron in a radar dish, which uses cavities and magnetic fields to force electrons to oscillate together. The universe must have its own natural klystron, operating on a scale we can barely conceive. The leading candidate is a process called a synchrotron maser. Imagine a supersonic shockwave plowing through a magnetized plasma. As charged particles like electrons get caught in this violent front, they are whipped into a frenzy, spiraling wildly along the magnetic field lines. Under just the right conditions of density and magnetic strength, these particles can be forced to radiate in phase, their tiny radio whispers synchronizing into a collective shout. It is the cosmic version of a feedback loop in a sound system, where a chance alignment of waves gets captured and amplified into a deafening screech. Another possibility involves the sudden, catastrophic reconnection of magnetic field lines near a magnetar. When these immensely powerful lines snap and reconfigure, they can accelerate bunches of electrons to near light speed in a perfectly coordinated manner, like a school of fish suddenly darting in the same direction. The key in all these models is the requirement for a perfectly tuned environment, a specific combination of magnetic field strength, plasma density, and shock velocity to trigger that rare state of coherence. It is a delicate balance amidst unimaginable violence, a natural amplifier that turns a chaotic explosion into a piercing, coherent scream. This single physical requirement may be the reason fast radio bursts are so rare and why we see them in such specific environments. The universe can shout in many ways, but to make a laser-like beam that cuts across billions of light years, it needs to build a perfect and perfectly destructive natural amplifier. That coherent scream often leaves behind a ghost, a faint but steady whisper that lingers long after the brilliant flash has faded. This is the mystery of the persistent radio sources, the enigmatic, constant glow of radio waves found at the exact location of some repeating fast radio burst. It is not the burst itself, but a quiet companion, a campfire that never goes out. The most famous examples are the original repeater, FRB 121102, and another prolific source, FRB 190520b. Both sit at the heart of a faint, smudgy radio glow that telescopes can detect at any time, whether the source is actively bursting or silent. This persistent emission is a vital clue, a signpost pointing to the environment that cradles the violent engine. So what is this constant radio hum? One compelling explanation paints a picture of cosmic youth and chaos. Imagine a young magnetar, perhaps only decades or centuries old, born from a recent supernova. This newborn monster is not resting. It spins furiously, and its unimaginably strong magnetic field acts like a giant dynamo, driving a powerful wind of charged particles outward at nearly the speed of light. This wind slams into the surrounding debris, the expanding shell of gas and dust from the supernova that created it. The collision creates a permanent shock wave, a region where particles are accelerated to extreme energies, causing them to glow steadily in radio waves. This structure is called a pulsar wind nebula, and it would act as a persistent luminous fog enveloping the magnetar. Every time the magnetar has a starquake and produces a fast radio burst, that brilliant flash must punch its way out through this nebula, which could explain the extreme Faraday rotation we see as the signal gets twisted by the nebula's intense magnetic fields. But a magnetar nebula is not the only possible source of this steady light. Could the persistent glow come from something even more monstrous? Another possibility is an active galactic nucleus, the supermassive black hole at the center of a galaxy. If a fast radio burst source were located perilously close to such a black hole, perhaps within its accretion disk or a jet, the radio glow could be coming from that incredibly energetic environment. However, this seems less likely for the localized bursts we have seen. The host galaxies are often small dwarfs, not the massive giants typically housing powerful active nuclei, and the precise locations of the bursts are usually offset from the galactic center, not right at it. A third idea is that the persistent source is a relic, the shocked aftermath of an even larger, older explosion that created the conditions for the current bursts. Yet the fact that this glow is so tightly tied to the burst location and varies in sync with the bursting activity in some cases, strongly suggests it is directly powered by the same central object. This leads to the next puzzling layer. Why do some repeaters have this persistent glow while others do not? Is it a matter of age? Perhaps all fast radio burst sources go through a youthful phase where they are enshrouded in the bright nebula of their birth. During this time, they are hyperactive repeaters with a strong radio glow. As the magnetar ages over thousands of years, its spin slows, its wind weakens, and the nebula dissipates, fading from view. The bursts may become less frequent or cease altogether, or the source might transition into a quieter, more mature phase where bursts are rarer and lack a surrounding nebula. In this view, the presence of a persistent source is a sign of a cosmic toddler screaming inside its crib of stellar wreckage. Alternatively, the difference might signal two fundamentally different types of engines. Perhaps the ones with persistent emission are indeed young magnetars in dense nebulae, while the ones without are older neutron stars reactivated in binary systems, where the environment is cleaner and lacks that bright, glowing shroud. A persistent radio source is more than just a curious side effect. It is a direct window into the life cycle and the living conditions of these cosmic powerhouses. Its presence or absence tells a story about youth versus age, about isolation versus companionship, and about the long, fading echo of the violent birth that started it all. The persistent glow around a repeater is a signature of its youth, but the next discovery revealed a source that seemed to mock our growing sense of order. Designated FRB 190520b, this repeater was discovered by the 500-meter aperture spherical radio telescope, or FAST, in China. At first glance, it appeared to be a perfect twin to the original repeater, FRB 121102. It lived in a small, star-forming dwarf galaxy billions of light-years away, and it too was accompanied by a persistent, steady source of radio emission, that constant campfire glow. The similarities were so striking it felt like the universe was repeating itself, offering a second example to confirm our theories about young magnetars in turbulent nebulae. But as astronomers looked closer, the twin revealed itself to be a challenging doppelganger, one that introduced profound new wrinkles into the mystery. The first major difference was its astonishing activity. FRB 190520b is a hyperactive repeater of almost unbelievable intensity. During its most violent episodes, it has fired off bursts at a rate exceeding 500 per hour. That is more than one brilliant, sun-vanquishing flash every 10 seconds for hours on end. This level of sustained fury is unprecedented, suggesting a central engine of even greater resilience or a trigger mechanism stuck in the on position. The second and more perplexing difference lies in its local environment, revealed by a detail in its signal. Every fast radio burst has a dispersion measure, the total smear from its journey. This total is the sum of contributions from the intergalactic medium, the host galaxy, and the immediate neighborhood of the source itself. For most bursts, the vast majority of that smear comes from the long trip between galaxies. But for FRB 190520b, the math did not add up. Astronomers used the precise distance to its host galaxy to calculate how much dispersion the intergalactic medium should contribute. The number they got was far smaller than the total dispersion they actually measured from the burst. This meant an enormous amount of the signal's smear was coming from somewhere very local, from a dense, complex cocoon of plasma immediately surrounding the source. Its local dispersion measure is among the highest ever recorded. This paints a picture of an engine absolutely buried in its own turbulent wreckage, sitting in a far denser and more magnetized shroud than even the original repeater. It is as if one young magnetar is screaming from inside a modest shed, while this new one is screaming from the heart of a raging industrial factory. This dense local environment could explain its hyperactivity, perhaps by providing more fuel for shocks or creating constant triggers, but it also complicates the simple story. Why are two sources with such similar profiles, a dwarf host and a persistent glow, living in such drastically different immediate neighborhoods? Does this mean the persistent glow itself can come in different densities, signaling different stages or types of youth? FRB 190520b is a gift and a provocation. It confirms that the dwarf galaxy persistent source archetype is a real and repeating phenomenon in the cosmos. Yet, in the same breath, it demonstrates that within that broad category lies a wild diversity of detail. Each new source we pinpoint with exquisite precision does not just answer old questions, it inevitably asks new, more complicated ones, reminding us that every cosmic mystery, no matter how familiar it seems, has its own unique and challenging personality. The hyperactivity of those young repeaters in dwarf galaxies suggested a pattern, a link between fast radio bursts and stellar nurseries. Then came a detection that shattered that assumption entirely. Fast radio burst 2020-0120e was a repeater, but its home was not a chaotic, star-forming dwarf. It was found inside a serene and ancient retirement home for stars, a globular cluster orbiting the nearby spiral galaxy M81, just 12 million light-years away. This proximity made it the closest known extragalactic fast radio burst source, a golden opportunity for detailed study. But its location was a profound shock to theorists. Globular clusters are among the oldest structures in the universe, dense balls of hundreds of thousands of stars that formed over 10 billion years ago. They are celestial graveyards for stellar evolution, where massive stars died off eons ago. According to the prevailing theory, this should be the last place in the universe to find a fast radio burst. Young, highly magnetized neutron stars, or magnetars, are born from the explosive deaths of massive stars that live for only millions of years. In a globular cluster, all such stars vanished billions of years in the past. So what or who is screaming in this stellar retirement community? The discovery forced astronomers to consider radical alternatives, pathways to immense radio violence that do not require a youthful magnetar. One compelling theory points to the extreme density of the cluster itself. In such a crowded stellar environment, close encounters and collisions are far more common than in the sparse galactic field. Perhaps the source is an old, dormant neutron star that has been violently reactivated. A close brush with another star, or even a direct collision with a white dwarf or another neutron star, could suddenly spin it up, reignite its magnetic field, or trigger cataclysmic accretion, essentially shocking an elderly stellar corpse back into a temporary frenzy. Another, more exotic possibility involves a different type of compact object altogether, an accreting black hole. In the dense core of a globular cluster, a stellar mass black hole could be slowly pulling material from a companion star. The turbulent plasma in its accretion disk could, under the right conditions, generate the kind of coherent shocks needed for a fast radio burst. This would be a completely different engine from a magnetar, proving that the universe has multiple ways to create the same brilliant signal. White dwarfs, the Earth-sized cores of dead sun-like stars, also enter the picture. Certain types of magnetic white dwarfs, or those in tight binary systems where mass transfer triggers explosive flares, could potentially produce radio bursts, though whether they could reach the required energies is hotly debated. The existence of FRB 2020-0120e is a powerful reminder that our early theories were too narrow. It screams from a place where magnetars should not be, forcing us to widen the search for cosmic engines. It suggests that fast radio bursts are not a signature of one specific stellar phase, but a versatile phenomenon that can emerge whenever extreme density, strong magnetism, and violent interaction converge, whether in the cradle of a newborn star or the crowded dance hall of ancient stellar relics. This one source, by its very unexpected address, tells us the story of these bursts is far older and far more diverse than we ever imagined. Every burst journey is a census of the cosmos. That single number, the dispersion measure, is not just a distance estimate. It is a detailed inventory of every free electron the signal encountered. But this inventory is a combined total, a sum of three distinct contributions. First, the signal passes through the halo and interstellar medium of its own host galaxy, a thick soup of plasma. Then it embarks on its epic voyage across the vast, nearly empty intergalactic medium, the thin web of gas filaments connecting galaxies. Finally, just before it reaches our telescopes, it traverses the similar material within our own Milky Way. The total dispersion we measure is the sum of all three of these cosmic waypoints. For a single burst, these contributions are hopelessly tangled. We cannot tell if a high dispersion measure means the burst came from very far away, or if it simply passed through an unusually dense cloud in its own backyard. This is where the power of numbers transforms confusion into clarity. By localizing not one, but dozens of fast radio bursts at precise, known distances, astronomers can begin to perform a statistical miracle. They can start to disentangle the cosmic ledger. Think of it like this: if you measure the total weight of a shipment of identical boxes, but you do not know how much each empty box weighs, you are stuck. But if you weigh many shipments, each containing a different number of boxes, you can use math to figure out both the weight of a single box and the weight of the cargo inside. Here, each fast radio burst is a shipment. The known distance tells us how much intergalactic medium it should have passed through, which is like knowing the number of boxes. The measured total dispersion is the total weight. With enough bursts spread across different distances, the patterns emerge. The average contribution from our own Milky Way can be mapped and subtracted. The contribution from the host galaxies, while variable, can be averaged out statistically. What remains is the pure signal from the intergalactic medium itself. This is the census. By plotting the clean intergalactic dispersion against cosmic distance, astronomers get a direct measurement of the density and distribution of the universe's missing normal matter. They are not just confirming it exists, they are measuring how clumpy or smooth it is across vast scales. Is the warm-hot intergalactic medium a uniform fog, or is it concentrated in specific, dense filaments? The dispersion measures from a growing population of bursts suggest it is both, a diffuse background peppered with denser knots, exactly as simulations of the cosmic web predict. Each new localized burst is another data point, another core sample through the void, letting us take the temperature and density of the universe's most empty spaces. This turns every brilliant, mysterious flash into a precision tool, a flare sent up to illuminate the invisible architecture of everything. The census of electrons is a map of the present, but those same signals might hold the key to the universe's accelerating future. This speculative frontier asks if fast radio bursts could become the next great tool for measuring dark energy, the mysterious force causing cosmic expansion to speed up. To understand this, we must revisit the Magnetars relation, the observed link between a burst's dispersion measure and its cosmic distance. Because dispersion measures the total electrons along the line of sight, and the number of electrons should scale with the volume of space traversed, the relation is in principle a direct cosmic yardstick. If the Magnetars relation is tight and predictable, then a fast radio burst's dispersion becomes a direct indicator of its distance, independent of the traditional redshift method. This would make bursts phenomenal standardizable candles, or more accurately, standardizable rulers. Imagine having thousands of these rulers scattered across space and time. By comparing the distance we get from the dispersion measure to the distance we get from the host galaxy's redshift, we could measure how the expansion rate of the universe has changed over billions of years. Any discrepancy would reveal the influence of dark energy, which alters the expansion history. The potential is breathtaking, a chance to use these transient flashes to weigh the most elusive component of the cosmos. Yet the path is strewn with monumental challenges. The Magnetars relation is not a perfectly clean line, it is a scatterplot. The total dispersion is a messy sum of contributions from the host galaxy, the intergalactic medium, and our own Milky Way. The host galaxy contribution is the wild card, a source of noise that can vary dramatically from one burst to another. A burst from a dwarf galaxy with little interstellar plasma will have a very different host contribution than one from a massive spiral galaxy with a thick disk of ionized gas. To use bursts as precision tools, we must find a way to subtract this galactic noise, to isolate the pure intergalactic signal. This is where the dream of thousands of localized bursts becomes essential. With a vast statistical sample, the random variations from individual host galaxies should average out, revealing the underlying smooth relation dictated by the cosmology of the universe itself. Future telescopes like the Full Square Kilometer Array promise to discover and localize tens of thousands of bursts. This flood of data could let us calibrate the Magnetars relation with exquisite precision, turning each new flash into a data point on the grandest chart of all, the expansion history of the cosmos. It is a long shot, a promise on the far horizon, but it illustrates a profound shift. Fast radio bursts are no longer just things we try to explain. They are becoming instruments we can use to explain everything else. The hope for a homegrown monster flared brightly with fast radio burst 2022-1022A. When it flashed onto the scene, its coordinates sent a jolt of excitement through the astronomy community. The burst appeared to originate from a spot deep within the plane of our own Milky Way galaxy, that dense, star-filled band that stretches across our night sky. For a moment, it seemed we had finally caught a close one, a fast radio burst erupting from our own galactic backyard. The implications were staggering. A burst from within the Milky Way would be millions of times brighter in our telescopes than its distant cousins, offering an unprecedented, close-up view of the engine in action. Every instrument on Earth and in space could be trained on its location, searching for any faint afterglow, any neutrino, any whisper of a counterpart with a clarity impossible for a source billions of light-years away. The dream of a galactic Rosetta Stone felt tantalizingly close, but in science, initial excitement must always bow to careful analysis. The first clue that something was amiss lay in the burst signal itself. While its position on the sky pointed to the crowded galactic plane, its other properties told a different, more distant story. Astronomers turned to two key fingerprints, the dispersion measure and the scattering. The dispersion was significant, higher than what would be expected for an object simply embedded in the Milky Way's disk. More telling was the scattering, the twinkling effect caused by the signal passing through turbulent plasma. This burst was heavily scattered, its sharp millisecond flash smeared out into a longer, washed-out signal. In the dense, chaotic environment of the galactic plane, such extreme scattering is common as radio waves plow through countless nebulas, stellar winds, and supernova remnants. However, the amount of scattering observed was even more severe than typical for a Milky Way source. It pointed to an extraordinary amount of turbulent material along the line of sight. The pieces of the puzzle came together to paint a new, more humbling picture. Fast radio burst 2022-1022 was not a resident of the Milky Way. Instead, it was a cosmic flash from a galaxy far, far beyond our own, perhaps billions of light-years distant. Its brilliant beam just happened to be aimed directly through the thickest, most tumultuous part of our galaxy's disk on its way to us. Imagine a distant lighthouse, its beam shining across a vast ocean. If you stand on a shore shrouded in a dense local fog, the light will appear diffused and blurred. You might mistake its diffused glow for a nearby lantern, but the character of the light itself reveals its true, distant origin. That is what happened here. Our own galaxy's plane acted as that dense fog, scattering and delaying the signal, while the burst's intrinsic properties, its high dispersion and energy, betrayed its extragalactic pedigree. This case became a masterclass in cosmic interpretation and a warning against jumping to conclusions based on a single piece of data. The sky is a layered tapestry, and a simple direction on a two-dimensional map can be profoundly deceptive. An event that appears to be in the foreground can easily be a background titan, shining through the clutter of our own celestial neighborhood. It underscored the absolute necessity of measuring every possible property of a burst, its polarization, its scattering width, its spectral shape, and comparing them against detailed models of the Milky Way's interstellar medium. The disappointment of losing a potential galactic burst was tempered by a deeper lesson. It proved that even the most crowded, opaque regions of our own galaxy are not impenetrable walls. The universe's most brilliant flashes can punch through, their signals encoded with the story of two journeys, one across the intergalactic void and a final, turbulent passage through the starry fog of our own spiral arm. The search for a true Milky Way fast radio burst continues, but now we know to listen more carefully, to separate the local weather from the distant storm. The search for a counterpart in light has come up empty, so astronomers have turned to an even more elusive kind of messenger. If a fast radio burst truly represents one of the universe's most powerful particle accelerators, then it should not just scream in radio waves, it should also fire bullets. The hunt is on to link these flashes to neutrinos and cosmic rays, a multi-messenger approach that could finally reveal the engine's brutal heart. Neutrinos are ghostly subatomic particles that barely interact with matter, streaming through the Earth by the trillions every second. They are perfect cosmic couriers produced in the most violent environments, like the cores of supernova or the jets of black holes. If a fast radio burst engine involves the crushing of matter or the acceleration of protons to extreme energies, it should produce a burst of neutrinos as well. Giant detectors buried deep in Antarctic ice, like the Ice Cube Neutrino Observatory, are listening. When a bright, fast radio burst is detected, scientists immediately scour ice cubes' data from that precise moment and direction, looking for a single, telltale flash of Cherenkov light from a neutrino interaction in the ice. So far, after checking dozens of bursts, the result is a profound silence. No convincing neutrino counterpart has been found. This null result is not a failure, it is a powerful constraint. It tells us that if the fast radio burst engine is accelerating protons or atomic nuclei, a process called hadronic acceleration, it is not doing it efficiently enough to produce a neutrino flare we can detect from Earth. It pushes theorists toward models where the energy is channeled almost entirely into electrons and their associated radio emission, a cleaner, more electromagnetic explosion. The same story applies to ultra-high-energy cosmic rays, the most energetic particles known, whose origins are a century-old mystery. These are single protons or atomic nuclei carrying the kinetic energy of a professionally thrown baseball, all compressed into a subatomic speck. They are thought to be accelerated in places like the shock fronts of galaxy clusters or the jets of active black holes. Could fast radio bursts be one of their sources? To find out, scientists use vast arrays of detectors on the ground, like the Pierre Auger Observatory, which watches for the giant air showers these particles create when they strike our atmosphere. They look for cosmic rays arriving from the same direction as a fast radio burst at the same time. Again, the link has not been made. No cosmic ray has been definitively traced back to a fast radio burst event. This silence is another crucial clue. It suggests that while the fast radio burst engine is phenomenally good at making radio waves, it may be surprisingly poor at launching the kind of matter bullets that would create neutrinos and cosmic rays. The acceleration mechanism appears to be picky, favoring lightweight electrons over heavy protons. A single, solid detection would change everything. Imagine Ice Cube recording a high-energy neutrino just as CHIME catches a brilliant radio flash from the same patch of sky. That coincidence would be a smoking gun, proving the burst engine is a true cosmic hadron collider, capable of shredding matter and accelerating particles to the absolute limits. It would instantly validate a whole class of models involving catastrophic mergers or hypermagnetized plasma shocks. We would know not just that something exploded, but precisely how it tore matter apart at the most fundamental level. The ongoing silence, therefore, is a form of listening. It tells us the universe's most brilliant radio flashes are, in a way, strangely clean explosions, their unimaginable power focused into a coherent beam of light rather than a chaotic spray of nuclear shrapnel. The silence surrounding neutrinos and cosmic rays points to a clean, efficient engine, but the very existence of that engine in certain cosmic neighborhoods creates a deep temporal paradox. If repeating fast radio bursts are the tantrums of young magnetars, fresh from the supernova factory, we should only find them in galaxies that are actively building stars. A young magnetar is a newborn, and newborns only exist where stars are being born. Yet our growing map of host galaxies stubbornly refuses to obey this simple rule. We have found repeaters in tiny, chaotic dwarfs blazing with stellar birth, exactly as the young magnetar model predicts. But we have also pinpointed them in massive, tranquil galaxies where the era of rampant star formation ended billions of years ago. These are cosmic retirement communities where the massive stars that create magnetars through core collapse supernova died off eons in the past. This is the repeater age paradox. If the engine is young, why is it living in an old neighborhood? Conversely, if we try to solve the paradox by suggesting the engine is old, we face a different, equally daunting physics problem. A neutron star's ferocious magnetic field is thought to decay over time, fading substantially over 10,000 to 1,000,000 years. How could an ancient neutron star, billions of years old, possibly retain or regenerate the apocalyptic magnetic strength needed to power a fast radio burst? It would be like finding a 1,000-year-old battery that still holds a full explosive charge. To resolve this paradox, theorists have been forced to imagine more creative, delayed pathways to creating a magnetar-level engine, pathways that do not require a recent massive stellar explosion. One compelling idea is the binary neutron-star merger. Picture two old, cold neutron stars, relics from the galaxy's early days, locked in a slow, decaying dance. After billions of years, they finally spiral together and collide. The result of such a merger is typically a black hole, but under just the right conditions of mass and spin, the collision could instead produce a newborn magnetar, a hypermassive neutron star with a magnetic field freshly wound to impossible intensity by the violence of the impact. This would be a delayed birth. The galaxy itself could be ancient and quiet, but within it, a sudden, catastrophic merger creates a brand new, screaming magnetar from the corpses of two old ones. It is a cosmic phoenix rising from the ashes of stellar ghosts. Another delayed pathway is accretion-induced collapse. Imagine an old white dwarf, the Earth-sized cinder of a sun-like star. If it is in a binary system where it slowly steals material from a companion, it can gain mass. If it crosses a critical threshold, about 1.4 times the mass of our Sun, it can no longer support its own weight. In a fraction of a second, it collapses not into a typical neutron star, but directly into a magnetar. The immense gravitational energy released, combined with the dynamo action of the collapsing, spinning core, could generate a magnetic field of staggering strength from scratch. This engine is not a relic of youth, it is a sudden, violent transformation in old age. Both of these models elegantly solve the location problem. They allow a powerful, fast radio burst source to appear in any galaxy, young or old, because the trigger is not recent star formation, but a rare, stochastic event that can happen at any time in cosmic history. The old stellar population provides the raw materials, the white dwarfs and neutron stars, and the slow, patient workings of binary dynamics provide the timer. The repeater we see in a quiet galaxy might not be a million-year-old teenager, but a one-day-old infant born from a billion-year-old marriage of stellar remnants. This paradox forces us to see the cosmos not as a static collection of objects, but as a place of continuous, hidden transformation, where the most brilliant flashes can be the last gasps of ancient systems or the first cries of something entirely new, born from the slow-motion collisions of forgotten stars. The age paradox forces us to reimagine stellar life cycles, but to understand the engine itself we must zoom in, far past the millisecond flash, into the very heart of the signal. When astronomers dissect a single fast radio burst with the finest possible time resolution, a hidden architecture emerges. Many bursts are not smooth, singular blips. They are composed of multiple, even tinier flashes called subbursts packed within the main event. These subbursts can be separated by microseconds, and within them there is evidence of structure on the scale of nanoseconds. This is not just a detail, it is a profound constraint. The speed of light is the universe's ultimate speed limit. In 1 nanosecond, a beam of light can travel only about 30 centimeters, roughly the length of a ruler. For a signal to show coherent variations on that timescale, the entire emitting region must be smaller than the distance light can travel in that time. Otherwise, the signal would smear itself out. This means the part of the engine that creates these brilliant, universe-spanning flashes is physically tiny, perhaps no larger than a football field. Think about the sheer insanity of that scale. An object the size of a sports stadium, located billions of light years away, can produce a radio blast bright enough to be detected across the cosmos. This microscopic origin point forces two incredible conclusions. First, the energy density at that spot is almost beyond physics, a concentration of power that defies everyday analogy. Second, and more importantly, it tells us the emission process must be highly organized, a coherent maser or laser-like process where every particle radiates in perfect unison. A chaotic thermal explosion the size of a star would never produce such sharp nanosecond features. Its light would be a smooth wash. Only a perfectly synchronized dance of electrons within a tiny, magnetized volume could create such a piercing, coherent spike. This microscopic signature is our clearest view into the engine's heart, proving it is not a vast, burning cloud, but a precise and monstrously efficient natural antenna. To find a possible analog, we look closer to home to a famous pulsar in the Crab Nebula. The Crab pulsar occasionally emits what astronomers call nanoshots, bursts of radio waves that last only a few nanoseconds. These are thought to come from lightning-fast sparks or plasma instabilities in the pulsar's intensely magnetized atmosphere. A single Crab nanoshot, if placed at a cosmological distance, would be completely undetectable, far too faint. But what if the process that creates a Crab nanoshot could be scaled up by a factor of millions or billions? What if, around a supermagnetar, the magnetic fields are so strong and the plasma densities so extreme that these nanosparks become nano-infernos? A fast radio burst could then be the combined output of thousands or millions of these scaled-up nanoshots firing in rapid succession, creating the microsecond and millisecond structure we see. This model elegantly connects the known to the extreme. It suggests the engine behind a fast radio burst is doing something fundamentally similar to our local pulsars, but in an environment where every parameter is dialed to 11, turning a tiny spark into a cosmic beacon. The nanosecond structure is more than a curiosity. It is a direct measurement, a ruler we can hold against the storm, telling us that within the maelstrom there exists a realm of perfect, terrifying order no bigger than a city block. That microscopic origin point, a cosmic stadium screaming across the universe, cannot be a singular fluke. If such a tiny engine can be seen from billions of light years away, then logic demands there must be countless others, their beams sweeping through the darkness. This leads directly to a profound statistical puzzle, the mystery of the event rate. How many of these brilliant flashes are actually striking our planet every single day? The answer is not simple because our telescopes, even powerful ones like CHIME, see only a narrow slice of the sky and a limited range of radio frequencies. They are like a network of security cameras watching a few specific street corners in a vast, dark metropolis. To estimate the total activity across the entire celestial sphere, astronomers must perform a cosmic extrapolation. They take the number of bursts they actually detect, factor in their telescope's field of view, its sensitivity, and the fraction of time it spends observing, and then scale that up to a full sky 24-hour operation. The results of this calculation are staggering. Conservative estimates suggest at least several hundred fast radio bursts occur over the entire sky every day. More aggressive models, accounting for bursts that might be fainter or at frequencies we do not monitor well, push that number into the thousands. Think about that for a moment. Every day, our planet is silently peppered by hundreds, perhaps thousands of these cosmic gunshots, each one a catastrophic release of energy from a distant galaxy. Most pass by completely unnoticed, their brilliant radio light washing over our silent planet because no telescope happened to be pointed in the right direction at the precise millisecond they arrive. This immense event rate transforms our understanding of what a fast radio burst represents. If they were once in a universe cataclysms, we would see a handful per century. The fact that they are a daily, even hourly, occurrence across the cosmos means they cannot be the rarest of events. Instead, they must be a relatively common, if brief, phase in the life cycle of certain cosmic objects. It is as if we have been listening to a forest at night and hearing random, deafening cracks. We first thought they were falling redwood trees, each one a final, singular crash. But when we realize the cracks are happening every few minutes, we understand we are not hearing trees fall. We are hearing the regular, violent snapping of branches in a windstorm, a routine expression of stress in a living, dynamic system. This commonality forces a sweeping conclusion about the population of their sources. The universe must be filled with a vast number of objects capable of this specific, terrifying feat. Given the energy requirements, magnetars or highly magnetized neutron stars are the prime suspects. Our Milky Way alone is known to host several dozen magnetars, and we suspect there are many more lying dormant or unobserved. If even a small fraction of these enter an active phase where they produce fast radio bursts, and if every galaxy has a similar population, then the math begins to work. The daily shower of flashes we infer becomes the collective tantrum of a universe teeming with magnetic monsters. Each galaxy, from the largest spiral to the tiniest dwarf, might have a handful of these objects crackling with pent-up energy at any given time. The event rate is not just a number, it is a census. It tells us that the extreme physics required to make a fast radio burst is not a bizarre exception. It is a regular, almost mundane part of how the universe channels and releases energy through its most dense and twisted stellar remnants. The sky is not quiet. It is a constant, invisible fireworks display of dying stars and woken ghosts, a testament to a cosmos that is far more violently alive and far more strangely repetitive than we ever dreamed. That constant, invisible fireworks display forces us to listen with incredible care, because the universe is not the only thing making noise. The hunt for these cosmic whispers is a constant battle against false alarms, a struggle to separate the signal from an ocean of terrestrial static. This is the frustrating and sometimes hilarious world of instrumental and terrestrial mimics. For every genuine fast radio burst that reaches the databases, dozens of imposters are caught and discarded. The most infamous of these are puritans, signals named after a mythical hybrid creature because they seemed part terrestrial, part celestial. For years, these millisecond radio bursts baffled astronomers at the Parkes telescope in Australia. They had the telltale dispersion sweep of a distant cosmic signal, but they only appeared during weekday working hours, never at night or on weekends. The mystery lasted for over a decade, fueling speculation about atmospheric phenomena or secret military experiments. The solution was both mundane and brilliant. A team of scientists finally traced the source not to the heavens, but to the observatory's staff kitchen. The puritans were produced when someone opened the door of a microwave oven before the timer had fully finished. The aging appliance leaked a brief pulse of radiation that, when it reflected off the observatory's moving metal dish, was smeared into a perfect mimic of an intergalactic fast radio burst. The discovery was met with equal parts relief and face-palming humor across the astronomy community. But microwaves are just the beginning. Our modern world is a cacophony of radio pollution. Satellite downlinks, sweeping radar beams from air traffic control and military installations, and even electronic glitches in the telescope's own hardware can produce sharp millisecond spikes in the data. A passing aircraft transponder, a spark from a faulty power line miles away, or a cell phone tower's momentary blip can all masquerade as a cosmic event. One observatory spent weeks chasing a strange, repeating signal that turned out to be the rhythmic pulse of a nearby electric fence charger. The challenge is that these signals often arrive at the telescope from above, reflected off aircraft or scattered by the atmosphere, so they do not have the obvious, constant signature of a ground-based transmitter. They can appear to come from any point in the sky, To combat this, astronomers have built a fortress of verification. The first and most critical line of defense is the coincidence check. A true cosmic fast radio burst will be seen by multiple telescopes separated by vast distances, because its source is so far away that its wavefront is essentially a flat plane washing over the entire Earth. If a sharp burst is detected at the Green Bank Telescope in West Virginia, but not at the simultaneous observation happening at the Arecibo site in Puerto Rico or the CHIME array in Canada, it is immediately flagged as local interference. Real-time data pipelines now cross-check detections across continents in seconds. Next, analysts examine the signal's polarization and its detailed frequency structure. Many terrestrial signals have a pure, narrowband tone, while a true burst smeared by the intergalactic medium has a broad, clean sweep. They also look for the signal's arrival direction. If it moves with the telescope as it tracks the sky, it is local. If it remains fixed against the background stars, it is cosmic. This rigorous, multi-layered vetting is the unsung hero of the field. It turns the chaotic static of our own noisy planet into a filter, a process that ensures every flash that makes the official catalog has earned its place. It is a reminder that to hear the faintest whispers from the edge of the universe, we must first learn to silence the deafening chatter of our own world. While our own world creates a static of false alarms, a giant ear in China has been listening with unprecedented sensitivity, cutting through the noise to hear the faintest whispers of the cosmos. This is the 500-meter aperture spherical radio telescope, known as FAST, a single, colossal dish nestled in a natural karst depression. Its sheer physical scale is breathtaking, a bowl of steel mesh wider than 5 football fields laid end to end. This immense size gives it one overwhelming advantage: raw collecting power. FAST can gather radio photons from the universe with a sensitivity no other instrument on Earth can match. Where other telescopes might only hear the loudest cosmic shouts, FAST can detect the murmurs, the faint sighs, and the distant conversations. In the hunt for fast radio bursts, this has been transformative. Before FAST, our census was biased toward the most energetic, blinding flashes, the tip of the cosmic iceberg. FAST has the power to see the iceberg itself, revealing the vast, faint population that was previously invisible. Its most stunning contributions have been with the repeaters. While telescopes like CHIME excel at scanning the whole sky to catch the initial flash, FAST can then turn its immense, focused ear to a known repeater's location and listen with profound patience and depth. When it does, it often finds that what other instruments saw as occasional outbursts are, in fact, near constant tantrums. A source that might fire once per hour for CHIME can be revealed by FAST to be producing dozens, even hundreds, of sub-threshold bursts in that same period. It is like using a sensitive microphone to listen to a geyser from a distance. You might only hear the biggest eruptions, but with FAST, it is as if you have placed a stethoscope directly on the ground, hearing not just the main blast, but every gurgle, every bubble, every tiny precursor and aftershock in the plumbing below. This hyperactive state, this constant low-level crackling, is a crucial new piece of the puzzle. It tells us that for some of these engines, the violent release of energy is not a rare, catastrophic accident, but a continuous state of agitation. The central object might be in a persistent crisis, its crust constantly microfracturing or its magnetic field endlessly flickering, with only the largest of these disturbances rising to become the brilliant burst seen by other telescopes. Fast monitoring of the original repeater FRB 121102 and the hyperactive FRB 190520b has provided a statistical treasure trove showing how burst energy, wait times, and rates are distributed. This data is the key to understanding the underlying trigger mechanism, whether it is a slow buildup of strain followed by a sudden release, like an earthquake, or a more random, Poisson process like popcorn popping. Furthermore, by discovering entirely new, faint repeaters that other telescopes missed, FAST is building a more complete demographic picture. It is showing us that the universe may be filled with far more of these objects than we thought, many of them quietly simmering at low power, only occasionally mustering a scream loud enough for the wider world to hear. The telescope's sensitivity is so great that it even raises a tantalizing, futuristic possibility. Could it one day detect the faint, dispersed afterglow of a burst that passed through the galaxy days or weeks before, a kind of cosmic echo? For now, FAST's primary role is that of the ultimate listener. Its vast bowl turned toward the heavens, patiently teaching us that in the realm of cosmic explosions, the loudest screams are only a small part of a much richer and much chattier conversation. The faint whispers and loud screams captured by our most sensitive telescopes carry more than just raw power. They carry a hidden orientation, a subtle twist that reveals the very nature of the storm. This is the story told by polarization, a property of light as fundamental as its color or brightness. To understand it, think of a radio wave not as a shapeless ripple, but as a vibration with a specific direction, like a rope being shaken up and down or side to side. This direction is its polarization plane. When light is linearly polarized, all its waves vibrate in the same plane. When it is circularly polarized, the plane rotates like a corkscrew as the wave travels. Most natural light in the universe is an unpolarized jumble of every possible orientation, the chaotic glow of a hot object. But the radio waves from a fast radio burst are different. They arrive with a striking, often extreme degree of polarization, a clear sign they were born in a highly organized, magnetized environment. The polarization is not static either. During the few milliseconds of a burst, the angle of polarization can swing wildly, sometimes completing a full 180-degree rotation. This rapid, coherent sweep is like watching a compass needle spin frantically in a hurricane of magnetism. It is a direct fingerprint of what physicists call a relativistic plasma, a soup of particles moving at nearly the speed of light, threaded by a magnetic field of unimaginable strength. The only place we know of in the universe that can create such conditions is the immediate vicinity of a magnetar. In that hellish zone, the magnetic field is so intense it forces any radiation escaping from it to be born with a specific, ordered polarization. The wild swings in angle then tell us the story of the field's geometry. If the polarization angle rotates smoothly during the burst, it suggests we are seeing emission from a region where the magnetic field lines are themselves twisted, like a bundle of ropes, and our viewing angle is cutting across that twist. The rate of the swing gives us a measure of the sweep of those field lines. In some bursts, the polarization remains remarkably constant, which could mean we are looking almost directly down the barrel of a magnetic pole, a clean, focused view into the heart of the beast. Furthermore, the mix of linear and circular polarization within a single burst is a detailed map. A high degree of circular polarization often points to propagation through a dense, magnetized plasma right at the source, where the waves themselves are transformed as they fight to escape. By decoding these subtle twists and turns in the radio signal, astronomers are performing a kind of remote magnetic tomography. They are not just detecting a flash, they are mapping the invisible architecture of the magnetic fury that created it, confirming that at the center of this millisecond cataclysm lies an object where magnetism is not just a feature, it is the dominant, shaping force of reality. That magnetic fury leaves a clear mark on the radio waves, but the rest of the light spectrum tells a different, quieter story. The absence of a bright, lingering glow in optical and infrared light is one of the most persistent and telling silences in the entire investigation. If a fast radio burst were truly tied to a traditional, cataclysmic stellar explosion, like a supernova or the tidal disruption of a star by a black hole, the aftermath would be impossible to miss. These events are not subtle. A supernova can outshine its entire host galaxy for weeks, leaving behind a brilliant, expanding shell of hot gas that glows brightly in visible light for months or even years. A tidal disruption event creates a months-long flare of ultraviolet and optical light as the shredded star's material spirals into the black hole and heats up. In either case, the fast radio burst would be just the opening act, a brilliant flash of radio preceding a long-running, spectacular light show across multiple wavelengths. Yet, when telescopes like the Zwicky Transient Facility or the Panoramic Survey Telescope and Rapid Response System swing to the locations of fast radio bursts, especially the repeating ones, they almost never find that expected afterparty. The sky remains dark. This is not for lack of trying. These optical surveys scan the entire visible sky every few nights with deep sensitivity. They are designed to catch anything that changes, flickers, or brightens. When a fast radio burst is localized, astronomers comb through the survey archives, looking for any transient optical source that appeared at that exact spot in the days, weeks, or months surrounding the radio flash. The limits they set are incredibly stringent. For a typical burst billions of light-years away, they can rule out an optical counterpart even 100 times fainter than a standard supernova. This profound absence is a devastating blow to many simple cataclysmic models for the repeating sources. It tells us that whatever is firing over and over again is not destroying itself in a brilliant fireball. The engine is not a one-time bomb, it is a durable machine. The energy released in the radio flash, as staggering as it is, represents only a tiny, specialized fraction of the total energy in the system. Imagine a lightning bolt. The brilliant flash and thunderclap are terrifying, but they represent only a small portion of the total electrical energy discharged in the storm cloud. The rest goes into heating the air, creating ozone and other processes. Similarly, the fast radio burst seems to be a highly efficient, focused release of a specific type of energy, coherent radio waves, while wasting almost nothing on the broad-spectrum thermal glow that would light up the optical and infrared sky. This forces the engine to be something that can convert stored energy directly into this coherent stream, without the messy intermediate step of heating vast amounts of material to incandescence. A Magnetar starquake fits this beautifully. The energy is stored in the immense stress of the star's crust and magnetic field. When the crust cracks, that stress is released almost directly into accelerating particles along magnetic field lines, producing the radio maser. Very little of it goes into heating ordinary matter to the millions of degrees needed to shine in X-rays or visible light. The missing optical glow is not an observational failure, it is a loud and clear message about efficiency. It tells us we are listening to a precision instrument in the cosmos, a natural laser that wastes no energy on anything but its piercing, focused beam. Every empty search deepens the mystery, narrowing the path to a solution where violence and elegance exist in a terrifying, radio-only balance. The missing optical glow tells a story of clean, efficient engines, but that story takes a sharp turn when we finally catch a one-off burst in the act and trace it home. For years, the repeating fast radio bursts were the only ones we could pin to a specific galaxy, because their predictable nature gave us time to aim other telescopes. The solitary, one-off flashes remained frustratingly anonymous, brilliant ghosts with no cosmic address. That changed with fast radio burst 2019-0523A. Detected by the Australian Square Kilometre Array Pathfinder ASKAP, this was a single, powerful blast with no repeats, but ASKAP interferometric power is immense. In that single millisecond, its network of dishes triangulated the burst's position with exquisite precision, handing astronomers a tiny, unambiguous dot on the sky. The follow-up was swift. The world's largest optical telescope swiveled to stare, and what they found was a revelation. The host was not a tiny, chaotic dwarf galaxy. It was a massive, mature spiral galaxy, a calm and orderly metropolis of ancient stars over 3.5 billion light-years away. This was a completely different cosmic neighborhood from the turbulent stellar nurseries that housed the famous repeaters. The implications were profound. Here was direct proof that a single cataclysmic event could produce a fast radio burst. The engine behind this flash was almost certainly destroyed in the process because it never fired again. And it did so in an environment where the frenetic birth of new stars, and therefore the creation of young magnetars, had largely ceased billions of years prior. This localization was a crucial piece of the demographic puzzle. It forced astronomers to accept that the fast radio burst population is not monolithic. We are not looking for one single type of cosmic engine. Instead, the universe seems to have at least two distinct pathways to creating these brilliant flashes. One pathway leads to the repeaters, the durable, tantrum-throwing engines often found in young, star-forming galaxies, likely powered by magnetars that survive their outbursts. The other pathway leads to the one-offs, the final screams from catastrophic events in older, quieter galaxies. These could be the mergers of neutron stars or the collapse of an overmassive star into a black hole, events that can happen long after a galaxy's peak star-forming era, using stellar remnants from its violent youth. The discovery of FRB 2019-0523 shattered the hope for a single, elegant solution. It confirmed a messy but thrilling cosmic reality. The universe speaks in fast radio bursts with more than one voice, using both the enduring fury of magnetic monsters and the final, brilliant notes of stellar annihilation to write its most fleeting messages across the dark. The search for a single, clean engine may be futile because the answer might not lie in the stars we can see at all. Beyond the familiar physics of magnetars and mergers, a more radical possibility whispers from the theoretical shadows. Could fast radio bursts be the signature of something entirely new, a crack in the standard model of particle physics? This is the speculative frontier where astronomers and particle physicists collide, exploring ideas where dark matter itself might be the hidden engine. One of the most intriguing candidates is a hypothetical particle called the action. Conceived to solve a deep problem in quantum chromodynamics, actions are also a leading candidate for the universe's missing dark matter. They are thought to be incredibly light, ghostly particles that barely interact with normal matter. But in the presence of an immensely strong magnetic field, a remarkable conversion can occur. An action could spontaneously transform into a photon, a particle of light. Now, imagine a universe filled with a sea of these dark matter actions, an invisible ocean through which galaxies swim. If a dense clump of this action dark matter were to drift into the extreme magnetic field surrounding a neutron star or a black hole, the conversion process could ignite. Not as a slow trickle, but as a sudden, catastrophic cascade. As actions convert to photons en masse, they could release a tremendous, coherent burst of radio waves exactly where the magnetic field is strongest. In this model, the magnetar or black hole is not the primary energy source. It is merely the catalyst, the anvil upon which the dark matter itself rings. The fast radio burst becomes a flashbulb illuminating the invisible, a direct detection of dark matter interacting not through gravity, but through a fundamental particle conversion. While deeply speculative, such models are not just mathematical fantasy, they are testable. If action conversion is the true source, it makes specific, sharp predictions. The properties of the burst, its duration, its frequency spectrum, and most importantly, its polarization, would be intricately tied to the strength and geometry of the host magnetic field in a way that differs from traditional plasma models. As we collect more bursts with detailed polarization data from instruments like FAST, we can search for these subtle fingerprints. A consistent deviation from the predictions of magnetar starquakes could point toward this more exotic origin. It is a long shot, but it exemplifies the profound shift in thinking these bursts have forced upon us. When nature presents a phenomenon that strains the limits of known physics, we must be brave enough to consider that the answer lies not in pushing our current models harder, but in stepping beyond them entirely into the dark. The dark matter whispers are a profound maybe, but the signal itself carries a more immediate truth about the galaxies it calls home. Every fast radio burst is a forensic probe, and its clues begin piling up long before it ever leaves its host galaxy. We have focused on how the dispersion measure maps the vast intergalactic web, but a significant portion of that total smear, and often the intense scattering that blurs the signal, originates right in the burst's own chaotic backyard. When the radio flash erupts, its first challenge is to escape the dense, turbulent interstellar medium of its host galaxy. This is not the thin, diffuse plasma between galaxies. This is a thick soup of ionized gas, molecular clouds, supernova remnants, and stellar winds, a bustling, messy metropolis of matter. As the signal punches through this environment, it interacts violently. Free electrons cause dispersion, slowing the lower frequencies just as they do in intergalactic space, but here the effect is concentrated and powerful. More dramatically, the signal encounters clumps and filaments of plasma of wildly varying density. These act like a hall of mirrors for radio waves, scattering the clean, coherent beam into multiple paths. Some waves take a slightly longer route around a dense cloud, others a shorter path through a clearer channel. By the time the signal finally escapes the galactic disk, it is no longer a sharp pulse. It is a scattered echo, its once crisp millisecond shape stretched and blurred, sometimes into a faint hiss lasting many seconds. This scattering width is a direct measurement of the turbulence and density of the host galaxy's interstellar medium along that specific line of sight. A heavily scattered burst tells us it came from a galaxy with a thick, chaotic disk of ionized gas, likely a young, star-forming galaxy buzzing with supernova explosions that churn the material. A burst with minimal scattering suggests a cleaner escape, perhaps from a galaxy with a more settled interstellar medium, or even from a source located far outside the galactic disk in the quieter halo. This is where a population study becomes revolutionary. If we can localize dozens, then hundreds of fast radio bursts to their host galaxies, we can start to sort them. We can place all the bursts from similar, massive spiral galaxies in one group, and all those from tiny, star-forming dwarfs in another. By analyzing the average scattering and the host galaxy portion of the dispersion measure for each group, we can build a statistical portrait of what the typical interstellar medium is like in each galaxy type. It is a completely new way of taking a galactic census. Traditional astronomy studies a galaxy's gas by looking for the faint light it emits or absorbs. But that only works for gas that is either hot enough to glow or positioned in front of a bright background source like a quasar. The fast radio burst method is direct and democratic. The burst itself is the brilliant background source, and it probes the galaxy along a random, pencil-thin beam from the inside out. It samples the galaxy's guts in a way we rarely can, revealing the total amount and the lumpiness of ionized gas along that random path. Over many such random samples, we learn the true, average conditions. Is the interstellar medium in dwarf galaxies as uniformly turbulent as we think? Do the spiral arms of grand design galaxies create predictable spikes in scattering? Each localized burst adds a data point, turning these brilliant mysteries into a network of interstellar weather stations, reporting back on the stormy conditions within galaxies billions of light years away. We are no longer just asking what causes the burst. We are using the burst to diagnose the health, the age, and the inner turmoil of its entire galactic home. The ultimate map of the cosmic web will not be drawn by a single brilliant flash, but by a relentless, daily storm of them. This future is being built right now in the quiet deserts of South Africa and the outback of Western Australia. The Square Kilometre Array, the SCAR, is not merely a new telescope. It is an entirely new way of listening to the universe. When its thousands of dishes and millions of antennas come fully online later this decade, it will possess a raw sensitivity and field of view that dwarfs anything we have today. Its promise for fast radio bursts is nothing short of revolutionary. Where current telescopes like CHIME might detect a few thousand bursts over years, the SKA is designed to find tens of thousands, perhaps even hundreds of thousands every single year. It will turn the occasional cosmic gunshot into a constant, deafening barrage, but the SKA will do far more than just count them. Its true power lies in instant, pinpoint localization. Using its vast interferometric network spread across continents, it will be able to determine the origin of a burst within milliseconds with an accuracy down to a fraction of an arcsecond. This is not just finding the right galaxy, it is finding the right neighborhood within that galaxy. The moment a burst is detected, its precise cosmic address will be broadcast across the globe in real time, triggering an instantaneous army of robotic followers. Optical telescopes, X-ray observatories, neutrino detectors, and gravitational wave interferometers will all swing into action within seconds, all staring at the exact same tiny point in the sky. For the first time, we will have a complete, simultaneous snapshot of a fast radio burst across the entire spectrum of physics. We will see if there is a fleeting optical flicker, a whisper of gamma rays, or a ripple in space-time that has, until now, always been just a little too faint or a little too fast to catch. This is the multi-messenger dream realized, where a single event is observed with every sense the universe provides. Beyond the SKA, a host of next-generation facilities are joining the hunt. The Vera C. Rubin Observatory, with its gigantic mirror and camera that will scan the entire visible sky every few nights, will be the perfect partner. It could catch the faint, fading afterglow of a burst in visible light that other telescopes miss, or rule it out with unprecedented certainty. In space, missions like the European Space Agency's Advanced Telescope for High-Energy Astrophysics, Athena, will bring a new level of sensitivity to the X-ray sky, searching for the high-energy counterparts that have so stubbornly refused to appear. Together, these instruments will transform fast radio bursts from tantalizing mysteries into routine celestial events. They will become standard tools in the cosmologist's toolkit. With a deluge of precisely localized bursts, the Mach-Watt relation will be calibrated to exquisite precision, finally allowing us to use dispersion as a direct, reliable measure of cosmic distance. We will map the warm-hot intergalactic medium in 3 dimensions, tracing the universe's hidden skeleton. We will understand the demographics of the engines themselves, learning if all galaxies, big and small, young and old, host these screaming objects and at what rate they awaken. The coming decade promises to shift our perspective entirely. We will stop asking what a fast radio burst is and start using what it tells us to answer the universe's oldest questions. The sheer number of flashes we see demands a terrifying efficiency, but it also forces a strange, almost philosophical question about our own place in the cosmos. Are we simply lucky to be looking at the right moment, or is the universe practically shouting to get our attention? This brings us to a subtle but profound geometric mystery, the question of the beam. We have talked about these events as cosmic lighthouses, but that analogy is incomplete. A real lighthouse sweeps its beam in a full circle, visible to any ship on the horizon. A fast radio burst source is more like a sniper's laser, likely firing a devastatingly narrow jet of coherent radio waves. The geometry of that jet dictates everything we see or fail to see. Think of it this way: if the beam is extremely narrow, say only a degree or 2 wide, then the vast majority of these cataclysms are firing their brilliant energy into the empty void, completely missing our line of sight. We would only detect the rare few where the beam happens to be pointed directly at Earth. In that scenario, the true cosmic event rate must be astronomically higher than what we observe. For every one flash we catch, thousands might be happening unseen, their energy wasted on the darkness. This would mean the universe is even more violently active than our already staggering estimates suggest. The opposite scenario is equally mind-bending. What if the beam is quite wide, perhaps tens of degrees? Then many more bursts would be pointed in our general direction, making our detection rate a more accurate census of the true activity. But this creates a monumental energy problem. To produce a signal bright enough to be seen from billions of light years away with a wide beam, the total power output of the explosion would have to be even more ludicrously high. It is the difference between a laser pointer and a floodlight. To illuminate a specific spot on a distant wall with equal brightness, the floodlight needs to consume far more total power because it is spraying light everywhere. A wide beam fast radio burst would require an engine of almost inconceivable fury to account for the brightness we measure. So we are caught in a cosmic balancing act, a trade-off between beaming and power. The observed rate and brightness of the bursts we detect are the only clues we have to solve it. By carefully analyzing the statistics, the distribution of energies, and the repetition patterns, astronomers can work backward. They can ask what combination of beaming angle and intrinsic engine power best fits the population we see. Current estimates are leaning toward a moderately narrow beam, perhaps only a few degrees across. This suggests we are indeed catching only a small fraction of the total fireworks display, but it also keeps the energy requirements for each individual engine within the realm of what a magnetar or catastrophic merger might just barely produce. It paints a picture of a universe filled with these cosmic snipers, most of their deadly shots missing us entirely, but with so many snipers firing so often that our planet is still constantly streaked with their near misses. This leads to a humbling, almost eerie thought. Our entire understanding of these phenomena, our maps of the cosmic web built from their signals, our theories about magnetars and mergers, all of it is based on a biased sample. We are constructing the rules of the game by only watching the players who happen to face our way. The true, hidden population of these events, the ones firing their beams into the endless dark, remains a silent majority, a ghostly chorus whose full power and purpose we can only guess at. The narrowness of the cosmic beam means we miss most of the show, but when a source does turn its spotlight directly on us, the data can be overwhelming. This was the gift of Fast Radio Burst 2020-01124A, a repeater that did not just speak, it delivered an entire encyclopedia. In a span of just 82 hours over several months, this single source erupted more than 2,000 times. It was not merely active, it was in a state of perpetual, glorious eruption, offering astronomers a statistical bonanza unlike any before. For the first time, scientists could move beyond studying individual, exotic flashes and instead analyze the behavior of a population, all from one engine. They could plot the distribution of energies, the waiting times between bursts, the shapes of the pulses, searching for the underlying mathematics that govern the tantrums. What they found was a system of breathtaking complexity, governed by what appears to be two distinct processes, one producing random, weaker bursts and another generating rarer, more energetic outbursts. It was as if this cosmic machine had both an idle chatter and an occasional, full-throated scream running on separate timers. This rich data set allowed researchers to test models with unprecedented rigor. The patterns strongly disfavored a simple, ticking clock like a spinning pulsar. Instead, they pointed to a magnetically dominated engine, perhaps a magnetar, where bursts are triggered by a cascading release of stress, like avalanches on a mountainside of magnetic energy. The sheer number of events revealed the inner rhythm of the avalanche, showing how small slips can lead to larger collapses in a chaotic, yet statistically predictable, dance. But the story told by the burst count was only half the narrative. the other half was written in the light's hidden twist, its polarization. As each of those 2,000 bursts flashed, the orientation of its radio waves swirled and danced in a frantic yet patterned ballet. The polarization angle often rotated dramatically within a single millisecond pulse, a phenomenon known as Faraday conversion. This is the signature of a signal fighting its way out of an incredibly dense, magnetized plasma, where the very nature of the light is transformed by the fury of the environment. The fact that this complex polarization behavior repeated with variations across thousands of bursts was a direct probe into the stability and structure of the magnetic maelstrom surrounding the source. It painted a picture of a dynamic, storm-racked magnetosphere where each burst was a lightning strike within a permanent and tangled magnetic hurricane. Then came the final, crucial piece of context, its home. When optical telescopes pinpointed its host, they found not a tiny, star-forming dwarf, but a grand spiral galaxy remarkably similar to our own Milky Way, complete with a central bar structure. This was a mature galactic metropolis, a place of order and relative calm compared to the chaotic dwarfs that host other famous repeaters. The discovery was a pivotal reminder of diversity. It proved that hyperactive, magnetically complex engines are not exclusive to one type of galaxy. They can ignite in the majestic spirals that define the cosmic mainstream. This one source, with its 2,000 voices and its familiar galactic address, became a microcosm of the entire fast radio burst mystery. It showed that the engine is durable enough for thousands of eruptions, complex enough to produce intricate polarized signals, and versatile enough to exist in a common type of galaxy. It refused to be pigeonholed, demonstrating that the universe builds these brilliant, chatty monsters in many neighborhoods, and when we are lucky enough to listen closely, they teach us not just about their own violent hearts, but about the ordinary galaxies they call home. 2,000 voices from a single source teach us about magnetic avalanches, but the ultimate cosmic cataclysm has long whispered a different promise. In the frantic search for counterparts, one early and thrilling hypothesis linked fast radio bursts to the universe's most luminous explosions, gamma-ray bursts. These are titanic flashes of high-energy gamma-ray light, lasting from milliseconds to minutes, signaling the birth of black holes or the collisions of neutron stars. The idea was beautifully simple. A short gamma-ray burst, thought to be produced when two neutron stars merge, should unleash a fireball of radiation across the electromagnetic spectrum. Could the fast radio burst be the missing radio scream from that same violent merger, arriving at Earth a heartbeat later? Finding that link would be a monumental unification, tying together two of the most energetic and mysterious phenomena in the cosmos with a single, catastrophic event. The hunt began with intense hope. Astronomers started cross-referencing the sky positions and detection times of known gamma-ray bursts with the logs of radio telescopes. A few tantalizing coincidences emerged. In one case, a weak radio pulse was found in archival data roughly 2.5 hours after a short gamma-ray burst. In another, a fast radio burst detection appeared to come from the same general direction as a gamma-ray burst recorded years earlier. For a moment, it seemed the puzzle was solved. These were the death cries of neutron stars, heard first in gamma rays and then in radio, but coincidence is not causation. The vastness of the sky makes chance alignments inevitable. As more data poured in, the consistent link failed to materialize. The vast majority of short gamma-ray bursts have no detected fast radio burst following them. And the overwhelming majority of fast radio bursts have no preceding gamma-ray burst signal. The dream of a clean, one-to-one match began to fade. The observational challenge is immense. Gamma-ray burst detectors like NASA's Swift and Fermi satellites see the entire sky, but they can only localize a burst to a region that might contain hundreds of galaxies. Radio telescopes, with their narrow fields of view, are rarely pointed at that exact region at the exact right time to catch a fleeting radio flash that might follow. It is a cosmic coordination problem of staggering difficulty, like trying to have two people in different cities witness the same lightning strike through keyholes pointed in random directions. Yet the theoretical possibility remains compelling. If a neutron star merger does produce a fast radio burst, why don't we see it more often? The answer may lie in that narrow beaming we discussed. The gamma-ray burst is believed to be emitted in a tight jet. The fast radio burst, if it comes from a different process in the merger's turbulent aftermath, might be beamed in an even tighter cone, pointed in a slightly different direction. From most angles in the universe, you might see one or the other, but rarely both. Only if Earth lies in the sweet spot of both beams would we witness the full multi-messenger spectacle. A definitive detection would change everything. Imagine the scenario. A gravitational wave observatory feels the space-time ripple of two neutron stars colliding. Seconds later, a gamma-ray satellite catches the brilliant flash, and within milliseconds or minutes, a radio telescope records a fast radio burst from the same pinpoint in the sky. That single event would confirm the engine, measure the environment, and unify three separate windows on the universe into one coherent story of stellar death. Until that day comes, the connection remains a haunting maybe. The silence is not a dismissal, but a constraint, telling us that if mergers do produce these radio flashes, they are either exceedingly rare, pointed away from us, or simply too faint for our current telescopes to see alongside the gamma-ray blaze. It is a reminder that in the cosmos, even the most violent endings can choose to whisper their final secrets in only one language at a time. Yet the hunt for these cosmic connections is more than a scientific pursuit. It is a story that has leapt from the pages of academic journals and captured the wider imagination. Fast radio bursts have become a rare bridge between the esoteric world of astrophysics and the public's innate curiosity about the universe. Their very name is a masterstroke of science communication, a perfect blend of the technical and the thrilling. It tells you exactly what they are, fast radio bursts, while leaving the most important question deliciously unanswered: why? This simple, catchy label invites wonder in a way that a more obscure acronym never could. For students, they are a gateway. A young person hearing about a signal that crossed billions of light years, carrying the imprint of invisible cosmic webs, is not just learning a fact, they are being offered a mystery. That mystery has the power to ignite a passion for physics, engineering, and computer science, drawing a new generation into the quest to build the tools and write the algorithms that will solve it. The technological drive behind this quest is itself a story of human ambition. The need to catch these millisecond flashes has pushed engineers to design telescopes of unprecedented scale and cleverness. It spurred the creation of CHIME, a radical, fixed array that sees the whole sky, and it fuels the monumental international effort behind the Square Kilometre Array. These are not just scientific instruments, they are monuments to our collective desire to listen, built through global partnerships that span continents and cultures. This collaborative spirit extends beyond professional labs. In an inspiring move towards open science, teams have released vast datasets of telescope recordings to the public. Now anyone with a computer and curiosity can download real radio telescope data and run algorithms to search for the unique sweep of a fast radio burst hidden in the cosmic static. While no major discovery has been made by a citizen scientist yet, the very act of participating demystifies the process. It transforms the public from passive observers into active hunters, sharing in the excitement of the chase. Museums and planetariums weave fast radio bursts into their shows, not as a footnote but as a headline act, a contemporary mystery unfolding in real time. This public engagement creates a vital feedback loop. The fascination fuels support for fundamental science, which leads to new discoveries, which in turn deepens the public's sense of connection to the cosmos. A fast radio burst is more than a distant explosion. It is a spark, one that travels not just through space, but through the human mind, igniting wonder, driving innovation, and reminding us that the greatest mysteries are not meant for scientists alone, but for anyone who chooses to look up and wonder what else is out there flashing in the dark. That public fascination inevitably circles back to the most thrilling question of all, the one that turns every unexplained flash into a story. Could these be signals from an alien civilization? This is the SETI angle, the elephant in the cosmic room. The idea is intoxicating, and it has a famous predecessor. In 1977, a radio telescope scanning the sky for signs of intelligence recorded a 72-second burst of radio waves so powerful that the astronomer who found it circled the printout and wrote, "Wow." The signal was never seen again, and it remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. When fast radio bursts were first discovered, that same electric sense of possibility crackled through the public imagination. Here were brilliant, fleeting signals from deep space, seemingly engineered for maximum attention, crossing billions of light years. Could they be interstellar lighthouses, or perhaps the exhaust flares of unimaginably vast spacecraft? For a brief, thrilling moment, the idea could not be dismissed out of hand. Yet, as the data poured in, the cold, hard light of physics began to dim that speculative fire. Scientists now overwhelmingly favor natural explanations, not because they lack imagination, but because the evidence points decisively toward cosmic, not artificial, origins. The first and most critical point is the sheer, staggering energy involved. While it seems immense to us, the power required for a fast radio burst is well within the proven limits of known astrophysics. Magnetar starquakes, neutron star collisions, and plasma shocks around black holes can all, in theory, concentrate the energy of stars into a millisecond beam. Nature has the tools to build these cosmic amplifiers. An artificial signal, by contrast, would require a civilization to harness and focus that same apocalyptic power deliberately, a feat that seems almost comically inefficient for communication. Second, consider the distribution. Fast radio bursts come from everywhere, from tiny dwarf galaxies to massive spirals, from the young, chaotic universe to the old and quiet one. They are a universal phenomenon. If they were beacons or signatures of technology, we would expect them to originate from specific, perhaps more advanced types of galaxies, not from every corner of the cosmos indiscriminately. The universe appears to be manufacturing these flashes on an industrial scale, using a natural, universal recipe. Finally, and perhaps most damning for the beacon hypothesis, are the repeaters. If a civilization were building an interstellar lighthouse to announce its presence, why would it use a pattern that is so chaotic, so sporadic, and so incredibly wasteful? The famous repeater with its 16-day cycle is not a regular ticking clock. It is active for a few days, then silent for 12. A beacon meant to be found would be consistent like a pulsar, or would encode clear mathematical information. These bursts are screams of raw power, not carefully crafted messages. They lack the hallmarks of designed communication. So, while the alien hypothesis makes for wonderful science fiction, the scientific consensus is clear: fast radio bursts are a spectacular natural phenomenon. Yet, in a beautiful twist, this conclusion does not diminish their wonder. It amplifies it. The truth emerging from the data is in many ways stranger than any fiction we could invent. We are not listening to the deliberate calls of other minds. Instead, we are eavesdropping on the universe's own violent language, a language spoken in the crack of magnetic whips, the final collisions of dead stars, and the tremors of cosmic monsters. That reality of a cosmos filled with such routine, natural violence is in itself a profound and humbling message. It tells us that the universe is not a quiet, static place, but a dynamic and often furious arena where energy is focused and released in ways we are only beginning to comprehend. The search for their source is not a search for engineers, but for the fundamental laws of physics operating at their most extreme. And in that search, we may discover that nature is the greatest and most inventive engineer of all. The alien hypothesis fades, but the true story emerging from the data is, in its own way, more spectacular. After 50 interwoven mysteries, from the first archival ghost to the hyperactive repeaters and the silent, cataclysmic one-offs, we are left not with a single, elegant answer, but with a breathtakingly complex cosmic portrait. The grand unifying theory of fast radio bursts is not a simple equation. It is a framework of diversity, a recognition that the universe speaks this brilliant, fleeting language in multiple, violent dialects. The emerging picture, painted by thousands of detections and dozens of precise localizations, points to a vast population with at least 2 dominant branches on its family tree. On one branch, we have the repeaters. The evidence now strongly suggests that most, if not all, of these durable, chatty sources are magnetars, neutron stars with magnetic fields wound to universe-breaking intensity. But they are not all the same. Some are cosmic teenagers fresh from the supernova factory, screaming inside the bright, persistent nebula of their own violent birth. Others might be older, reactivated by the gravitational tug of a binary companion or by slowly accreting material from a stellar partner. Their complex environments, the dense plasma shrouds, the intense Faraday rotation, the turbulent scattering all point to a central engine embedded in a maelstrom of its own making. Their periodic cycles whisper of orbital dances, and their hyperactive states reveal engines of astonishing resilience. On the other branch are the one-offs. These solitary, devastating flashes likely represent the universe's finales. Many are probably the death cries of catastrophic mergers, like 2 neutron stars spiraling together, or the collapse of an overmassive star directly into a black hole. They are the brilliant, concluding notes in billion-year-old stellar sagas, events that destroy their source forever. This bifurcation elegantly explains the host galaxy diversity. The repeaters often, though not always, favor younger, star-forming galaxies where magnetars are born. The one-offs can appear anywhere, even in quiet, elderly galaxies, because they use ancient stellar remnants as their fuel. Yet, for all this progress, profound gaps remain, humbling reminders of how much we have yet to learn. We still do not know the precise emission mechanism, the exact physics that organizes a seething plasma into a coherent, universe-spanning laser beam within a region no larger than a stadium. We cannot fully explain why one magnetar becomes a prolific repeater while another, seemingly similar one, might only ever fire once. The environmental diversity is still baffling. Why do some magnetars sit in brilliant radio nebulae while others, in seemingly identical galaxies, do not? And what of the outliers, like the burst from the ancient globular cluster, which defies both the young magnetar and the cataclysmic merger stories? These are not minor details. They are the frontiers. The journey is far from over. Each new telescope, each new flash localized, each multi-messenger follow-up is not just filling in a blank. It is actively redrawing the map, challenging our categories, and revealing a universe more inventive and violent than we dared to speculate. The 50 mysteries are not 50 separate locks awaiting a single key. They are 50 threads in a single, magnificent tapestry, one that we are only just beginning to unravel, stitch by brilliant millisecond stitch. From that first ghost in the data to the daily storm of cosmic flashes, the journey through these 50 mysteries has revealed a universe far more dynamic and articulate than we ever imagined. Fast radio bursts began as a baffling anomaly, a single point of light that challenged our understanding of energy and distance. We have followed their trail through the echoing halls of distant galaxies, untangled the clockwork of their periodic dances, and felt the magnetic fury imprinted in their polarized light. We have met the durable repeaters, likely magnetars screaming inside their own stellar wreckage, and witness the final, brilliant cataclysms of the one-offs. We have turned their fleeting signals into maps, using them to find the universe's missing matter and to probe the turbulent hearts of galaxies billions of light years away. They are no longer just cosmic oddities. They have become tools, brilliant flashlights we can shine into the darkest corners of the cosmos, illuminating the invisible web that binds everything together. The story is not finished. With every new detection from telescopes like CHIME and FAST, and with the revolutionary power of the square-kilometer array on the horizon, we are not just solving a puzzle, we are learning an entirely new language the universe uses to speak about its own structure, composition, and violent history. The next great discovery, the one that finally links a burst to a gravitational wave chirp or reveals the true engine in microscopic detail, could be just 1 millisecond away. Our understanding of the cosmos is being rewritten in real time, in bursts of energy that cross billions of years to reach us. Which of these 50 mysteries left you most in awe? Was it the sheer power, the clockwork precision, or the idea that we are using these flashes to weigh the unseen universe? Share your thoughts and stay curious. The universe is still talking, and we are only just beginning to understand what it is saying.